So, preheating. Good. So, this is the picture. Okay, this is not working anymore, or not much. Inflation cures the hot Big Bang theory, but provides, more importantly, initial conditions for the primordial fluctuations, scalar and tensor. The tensor form an irreducible background, which can be boosted, enhanced, if you assume extra considerations. That's what we saw so far. Now, imagine we finish inflation, and we need to reheat the universe. We will see now in a moment what that is. So we need to match the end of inflation with the hot Big Bang thermal picture. And we are going to see that this leads naturally, in some cases, to a new gravitational wave production, which actually is very effective. Good, that's what we are going to cover now. So the picture is that we assume a period of exponential, quasi-exponential expansion, that's inflation. And then we know that the early universe before BBN was described by a thermal plasma of a relativistic species. So we need to match these two stages, and the matching is done, is needed if you want, because at the end of inflation, you only are left with vacuum energy, whatever is responsible for inflation, no? Typically in the form of potential energy of the inflaton. So we need to produce all these particles somehow that will thermalize. How we do that? Well, somehow the energy responsible for inflation needs to decay, whatever the process, into some particle species. This will decay or interact with other particles. Altogether, through interactions, they will reach thermal equilibrium, and then you match with the hot Big Bang theory. That's the idea. Good. How to implement this idea is, of course, possibly the most difficult problem in theoretical cosmology, because obviously, if we don't know what's the underlying microphysics for inflation, much less we know how to connect the inflationary sector with the matter sectors. Literally, this problem is about producing all the matter particles in the universe, everything that is out there. Okay? So obviously, we would need to have the knowledge of this Lagrangian, which obviously we don't. Okay? So we will have to speculate with simple situations. Good. So, simple situations, and you will see that still they are quite complex at the technical level. A scalar reheating, I assume I have a monomial potential for my inflaton, and I have a dotted field. I call it K. It's a singlet, a scalar, singlet under standard model symmetries. And there are situations where I can give it a mass or a symmetry breaking potential or something else. And I'm going to assume a simple coupling, symmetric, very basic coupling between inflaton and the dotted field. Now, before you tell me, oh, this potential is ruled out for inflation, yes, we know, it's ruled out for inflation. But we are not doing inflation now. We are doing reheating. So I'm only using this monomial form for reheating after inflation. Yet, we are going to call it chaotic scenarios, the ones that have this monomial shape, because historically they were called like that. All right? But it's just a terminology, a name. What we care is we are going to have this for after inflation. Good. Imagine you want to solve now the dynamics of this. You only need to solve these equations. These equations are, of course, very complicated. On the one hand, you have the zero mode of the inflaton, the homogeneous part. On the other hand, you have fluctuations of the inflaton and fluctuations of the dotted field. And they are coupled because they are interacting theories. This is an interaction between the two species. So obviously, this is really difficult to solve it in full generality. The dynamics are typically nonlinear. Furthermore, as we will see in a moment, the effects are non-perturbative and everything is occurring far from equilibrium. Okay, so it's all the most difficult ingredients you could think of for quantum field theory, you have them all together there, essentially. Okay? Now, the fact that the dynamics are typically non-perturbative, and we will see an example of this in a moment, it's what makes call this preheating with P instead of reheating. So reheating is the idea that I need to produce all the particles in the universe until they thermalize and match smoothly with the hot Big Bang theory picture. Preheating is whenever in this production of particles I have non-perturbative effects. It doesn't mean that I finish with the decay products thermalizing. It means that the production of them, as long as it's non-perturbative, then we call it preheating. It's just terminology, okay? Okay, 1 second. Good. Preheating. So now let's see examples of a scalar preheating. Let's see how this really operates. So again, we are going to assume this monomial shape. We are going to call this chaotic scenario. We could call it just monomial, but for historical reasons, we will keep the name chaotic, as I said. And we don't care about inflation for this shape. The shape during inflation is different than this. We are going to assume it for reheating. Okay? Good. Let's stick to call it chaotic. And essentially, the paradigmatic example in these scenarios, when you have a monomial potential, is called parametric resonance. So how does parametric resonance work? I have my inflaton here, slowly rolling the potential. As we said a number of times already, during inflation, the shape is not monomial, it's something else. For instance, alpha attractors that flatten out the potential. But we don't care about that now. What we care is that inflation ends once the inflaton reaches a given position, and then it's going to oscillate around the minimum of the potential, which depends, of course, on the shape of this monomial. So we let it oscillate. 2 is happily oscillating. But what happens that when it passes through 0, if now you look at the fluctuations of the Dotter field, chi and x are the same. These x are the Fourier modes of chi with some transformation, but essentially the Fourier modes. They have a time-dependent mass. And this mass is given by the interactions with the inflaton. And the inflaton is oscillating. So when it passes through 0, something magic is going to happen, which is the effective mass goes to 0, because it's proportional to the amplitude of the inflaton, which means the rate of change of the mass is maximum. So it's bigger than the mass square itself. This is the condition that we call violation of adiabaticity. So if I have an oscillator-like equation like this for the Fourier modes, but the effective frequency changes in time fast, which means this, then the solution is not a harmonic oscillator. The solution is going to be something unstable, with changing amplitude in time. And that's what happens. Due to violation of adiabaticity, we are actually going to excite very much these mode functions. They were happily being adiabatically evolving here in these regions, but once the inflaton crosses here, they don't evolve adiabatically anymore. Boom. This boom is translated into particle production. So this is a quantum phenomenon in which when I have a time-dependent background that my quantum modes enjoy, these are the fluctuations here, they are gonna be very excited when the time dependence is non-adiabatic. Okay? So this is basic principle of particle production in quantum field theory in a time-dependent background. In this case, it's not a background, it's the interactions through the inflaton. If you do this more technically, for instance, for the lambda phi to the 4th case, this is the equation of the Dotter fluctuations. The x is the same as the original Dotter field, you see, but with a conformal rescaling, and these are the Fourier modes. And the equation of motion essentially is this one, with this Jacobi cosine here, which is a periodic function, which is the solution of the oscillations of the inflaton in a phi to the 4th potential. Okay? Good. Here some couplings, don't really matter. If I do a step for m squared phi squared for the inflaton, the equation looks similar for the fluctuations of the Dotter field, but now the behavior of the inflaton is slightly different because it's a standard cosine function. So the point here is that in reality it doesn't matter whether I have phi to the 4th, phi to the 2 or something else. What it matters is I have a periodic function. And if you have a periodic change in your effective frequency, when the inflaton crosses 0, you are going to stimulate it non-adiabatically the excitation of the fluctuations of the Dotter field, necessarily. And now what happens? My inflaton is going to cross around 0 many times because it's oscillating. Okay? The oscillations are sustained for some time. So every time I cross through 0, I'm going to stimulate particle production. But whereas the first time I'm going to do it in vacuum because there were no particles, the next time, now I'm going to produce particles on top of the previously produced ones. So there's going to be, again, a production out of vacuum, but also a stimulate production out of the ones I had already stimulated. So altogether, when you start repeating this process, the result is that you have a resonant effect. And essentially, your solutions grow like this. exponentially. So the amplitude of certain mode functions, when I say certain is for certain momenta, not for all momenta, are gonna enjoy some resonance behavior and they are gonna grow exponentially fast, with the whole physics controlled by this exponent here, which is called the Floquet exponent. This is physics of the 19th century, and I'm not saying nothing fancy here, but of course now we are applying it in our context of quantum field theory. All right, but at the end solving these guys is physics of classical equations of motion, you know, you solve for the solution, and what you find is that depending on this Q parameter, this is called the resonance parameter, and the resonance parameter depends on the physical context, depends on the couplings or initial conditions. I don't want you to focus on the details now, but it's fixed once you have a model. Now you have a value for your resonance parameter given the couplings choice, and depending on Q, then your resonance, your Floquet exponent is very different. For instance, in this example, for natural momenta in the natural units, which is the frequency of oscillation of your field, the units in which to measure momentum, for this interval, I have a support for non-zero Floquet index, and everywhere else is 0, which means I'm going to have an instability for the modes which are within this band. Yeah, this is the phenomenon of resonance. It doesn't apply to all the frequencies, obviously. It only applies to certain range of frequencies. This is the manifestation of this, the Floquet exponent. So let's look at this example, maybe zoom in, and we see very clearly, you know, for modes that they belong within this band, they are going to have a sizable Floquet index, they are going to grow exponentially. Anything else outside, left or right, is not going to be excited, so it's going to remain in vacuum. Good, how does it look this in practice? So here I have a spectrum initially that represents vacuum fluctuations. This is the standard spectrum for vacuum fluctuations. If I would extend it all the way to infinity, I would have the standard problem of what do I do with my UV vacuum modes, okay, in quantum field theory. And then through normal ordering, well, you put them outside. In cosmology, we don't really know what to do with them. But in practice, what's happening here is that for a certain range of modes, you are going to take them out of vacuum. And you see here very clearly the resonance phenomenon. So this is the amplitude of the fluctuation, this is the spectrum versus k in the natural units of the problem. I've chosen a given Q, and then what we see is that there is instability band of the amplitude of the fluctuations growing exponentially fast within this narrow band. But, of course, once you pump enough energy, because this is an exponential process, once you pump enough energy, your initial condition was the total amount of energy you have in the system. At some moment, you cannot pump more energy than you have, so then the guy is going to back react into the dynamics. The dynamics is going to become nonlinear, and then you are going to spread out your spectrum, both to the infrared and to the UV, through a scattering of the modes. In other words, because of interactions between the fields, there's going to be a scattering of the modes because the physics become nonlinear, and then we propagate power to the UV. Another example, instead of starting with a narrow band, now for another choice of resonance parameter, I have an infrared band. So you take out of vacuum your modes, until you hit nonlinearities, and then you spread power to the UV through a scattering between the modes, because they are coupled and the system is nonlinear. All these plots that I'm showing you here are obtained, with a lattice simulation. So essentially, with linear physics, with analytics if you want, you could follow this exponential growth, but you really need eventually a lattice simulation to capture, something is going on. Okay, maybe it's because Carlos touched there. Yeah, you need a lattice simulation to capture the nonlinear physics, which is the spreading out of the spectrum to the UV, and eventually to understand in what shape it settles down. All right? So now imagine the picture in the early universe is that I stimulate, thank you so much. I stimulate some daughter field like this. It creates an out of equilibrium distribution, which is precisely this spectrum. And now you either wait until it equilibrates, or it interacts with other field species, or it decays into other field species and thermalizes. At this point, I'm still totally far out of equilibrium, which is this shape. Okay, this spectrum has nothing to do with the Einstein-Bose distribution. It's a totally out of equilibrium distribution. And now the funny thing is that we're going to see in a moment that all this process is going to produce a lot of gravitational waves. Good. So I have other processes. It's not only about parametric resonance. Imagine I have this situation where I have an inflaton which is happily rolling here during inflation along this valley. But this inflaton is coupled to a Higgs-like guy. So this chi is like a Higgs-like symmetry breaking field with symmetry breaking potential, like a Mexican hat potential. And it's interacting between the inflaton and this Higgs guy. And the interactions are also written here in this fashion. This is the original form of the interaction, but I rewrote it in this form. So you see that essentially, naturally, this kind of interaction defines a critical point, such that when the inflaton is above this critical point, then the Higgs field has a positive defined mass. But when the inflaton crosses this critical point and becomes smaller, this mass is going to become tachyonic. And essentially, that's going to trigger essentially the end of inflation. So the inflaton comes here, becomes smaller than the critical value. Critical value is given as a function of the constants, the coupling G between the Higgs and the inflaton, and the typical mass parameter of the Higgs, which is the square root of its self-interactions times the BEF in the true vacuum expectation value state. So essentially, you trigger an instability, and if you have a tachyonic mode, then what's going to happen that you're going to have again an exponential growth for a certain infrared band of momenta. Tachyonicness always implies that. If I have tachyonic mode, I grow exponentially. Of course, the growth is not indefinite. Eventually, it regularizes itself once it gets here. We will see that more in detail later on, because this is actually a phase transition, what I'm describing here. Once we get into phase transitions, I will describe this more in detail. Good. In summary, the physics of preheating is to look at oscillator-like equations of this kind with time-dependent and scale-dependent effective frequencies, such that these effective frequencies, whenever they violate adiabaticity, let this be due to tachyonic effect or simply because of periodic oscillations, then we are going to excite very much the modes. This means that for a specific range of momenta, the amplitude of the fluctuations, and hence if you want the occupation number, which is just quadratic in these fluctuations, are going to grow exponentially fast. This is amazing because I have embedded a natural instability in the system, which is going to produce a very inhomogeneous distribution of my field fluctuations. Why inhomogeneous? Because there's going to be a typical length, which is the inverse of the typical momenta that are being excited. The energy density contrast is going to be very high because I'm going to produce large macroscopic fluctuations, as you will see, and they are moving at relativistic speeds. How does it look? Just for you to have an image pictorially. This is the example of hybrid preheating that I was showing, the second example. I'm taking a two-dimensional slice of a space, and I'm plotting you the amplitude of the Higgs. Here phi and curly phi are the same, sorry about that. So this is a realization, a random realization of one of these exponential growth. It's like a bubble structure is growing, it keeps growing at a later time, eventually cannot grow any further due to energy conservation, and the reaches of that structure are starting to be propagated away. But at the same time, other bump structures are emerging because this is a stochastic process. These fluctuations are literally stochastic process, okay? That's the quantum mechanical nature of it. So eventually they collide, they start colliding, and they break apart through nonlinearities into smaller structures. So this process, energetically speaking, is very violent, very, very violent, and this is why preheating was understood soon enough, as soon as people understood this is what preheating was about, as a very effective gravitational wave generator. This is as close as you are going to get in the early universe to the idea in the late universe of having two black holes orbiting around each other. In the late universe, you have two black holes that approach each other. The closer they get, the more relativistic they become, and the more gravitational waves they emit. Here, I don't have isolated objects because I have a continuum field theory description, but I have these objects in the form of these bumps of the inhomogeneities of the large distribution of the Higgs. They are colliding at very energetic relativistic speeds, and hence they are going to produce a lot of gravitational waves. Okay? It's the same idea as a phase transition, but here I'm in preheating. Good, how do we do this? Since this is nonlinear and out of equilibrium physics, we have to do this in the lattice. In the lattice doesn't mean we do lattice QCD. We are not doing sampling of path integral. It means that we are following the classical equations of motion from initial quantum vacuum fluctuations. So we put initial conditions mimicking a spectrum, that of quantum vacuum fluctuations, and then we follow the dynamics according to the relativistic wave equations. Since the fluctuations I'm going to excite grow exponentially large, and as such, their occupation number also grows exponentially large, the field configuration becomes classical. It's pretty much the same as when you have a classical configuration of electromagnetism, which is made of photons at the level of individual quanta. But if you have trillions of them, you describe them with the Maxwell equations. This is the same. I'm showing you this for scalars. I could do the same for gauge fields. All right? At the same time, we have to solve for the expansion of the universe consistently, because these guys, here scalar fields, are responsible for the expansion of the universe at the end of inflation. So I have in a very large excitation of them, but at large scales, I still have homogeneity and isotropy. I'm only breaking that locally through this inhomogeneous distribution. But at large scales, of course, on the average, I'm not creating large scale fluctuations. These are still homogeneous and isotropic on the average. So what you have to do is to take the volume average of all these inhomogeneous energy and pressure distributions and then source your Friedman equations. If you capture these fluctuations in a box that is much larger than the typical wavelength of the fluctuations, then you are correctly describing the expanding universe context in which they are. Good, and at the same time, of course, we have to solve our favorite equation. So the gravitational wave equation as sourced by the transverse traceless part of the anisotropic stress, which in this case is the sum over gradients of the scalar field content, where we already know that Hij are transverse traceless degrees of freedom. We have to solve all of this simultaneously, and this is why we need the lattice. Because once the matter fields, the daughter fields, the inflaton, they become nonlinear dynamics, you can only follow this with a lattice simulation. Question to you guys. How do I compute the transverse traceless part here? Because it's not enough just to plug in this in the lattice. I need to extract the transverse traceless part. Question for lunch. Okay, I don't need you to answer right now, but this is homework for lunch. So think a little bit, how would I obtain the transverse traceless degrees of freedom? Good. How does it look, the gravitational wave background in any of these scenarios? Here is an example in the hybrid scenarios where I have an inflaton coupled to a Higgs-like guy. This is called hybrid preheating, and the omega gravitational waves as a function of momentum normalized to the natural mass of the problem, and as a function of time, it's shown here. It has a tachyonic instability. The Higgs field has a tachyonic instability, so the gravitational waves grow exponentially fast initially. Once the system becomes nonlinear, then it spreads out power to the UV. Eventually, it settles down into a relaxed spectrum. Good. The amplitude of this spectra can be redshifted till today with some formula. I'm not going to show the details of that. And essentially, you can determine that you can get very large amplitude today of the order of 10 to minus 11 in omega gravitational waves. That's considered a large amplitude. Because remember, for instance, the quantum vacuum fluctuations maximum amplitude I can tolerate from inflation is 10 to minus 16. This is 5 orders of magnitude above. So not bad. But the problem is that if I take natural values for the self-coupling of the Higgs-like field, say, for instance, the standard model self-coupling of order 0.1, Then the frequencies are gigahertz. So this is a high frequency background. I have the ability, if I tune my self-coupling to very, very small values, to perhaps reduce the frequency, but you see this requires a very fine-tuned situation, because imagine I want to make it observable at LISA, then it will be 10 to minus 40. And this is a ridiculous hierarchy of scales. So yes, I have the freedom to do it, not motivated, and it's very unnatural and very unlikely that anything like that is realized in nature. So realistically speaking, I would say these backgrounds are very nice, but not observable, at least with the current technology, okay, because they are doomed to be high frequency. Okay, let's see if with the parametric resonance, maybe we are more lucky. So this is the typical example of monomial potential of the inflaton. When it's oscillating, I have one Doppler field coupled to it, and then the Doppler field gets very excited, exponentially initially, then non-linearly, and it produces, typically it sources this exponential growth of gravitational waves until it opens up, well, it's not so clear in this picture, but it opens up through non-linearities to the UV, and it relaxes into a final spectrum. Let me call this a single bump spectrum, no? Because there is one maximum, eventually this tail turns around here, and there is a location of this maximum, and all the physics here, the height and location of the maximum of this spectrum, are controlled by the resonance parameter. All the physics is encoded in this resonance parameter. The strength of the coupling between the Doppler field and the inflaton, the initial amplitude of the inflaton at the onset of oscillations, and the curvature of the potential of the inflaton during oscillations. So you see, once you have a problem, microphysics problem, what's your potential, what's your coupling, then you can immediately find what is your Q, and this will tell you, through some parametrization that we worked out a few years ago, what is the height of your background today. So essentially now you don't even need to solve this in the lattice anymore. You just give the resonance parameter, and we have 4 master formulas to predict what's the height of the spectrum today. At the same time, you also need to predict, of course, at what frequency, which also depends on the resonance parameter. The amplitude in these scenarios can be even larger than before. It can reach 10 to minus 9. We believe maybe we could get close to 10 to minus 8 in some cases, but it's a bit borderline, so let me leave it in 10 to minus 9. Okay, very nice amplitude, but we suffer the same problem. Again, we are doomed to have everything at high frequencies. So why am I having everything at high frequencies? Because this is a reflection of the fact that the models I'm choosing are high energy scale models. So if you redshift the Hubble radius from a very high energy scale model of the order of Gatt scale till today, that's going to correspond to very high frequencies, close to gigahertz. And since this is causal physics, and I'm producing my physics inside the horizon, this is going to be even higher frequencies, shorter wavelength. So essentially in these scenarios, it seems impossible to really decrease the signatures to low frequency. It is an open problem in preheating to find a scenario where you can sustain this kind of non-perturbative effects at low energy scale. I haven't found it in 15 years, okay? Every time I think I find the solution, some effect comes and spoils the physics. But it's an open problem that I'm not willing to give up yet, that is not possible to figure out. Let me do following exercise for the sake of understanding. Imagine that we can think of placing these backgrounds at lower frequencies where we have detectors. Now, taking that hypothesis, I'm going to ask myself the following. If the amplitude of my background scales with the resonance parameter and hence the coupling like this, and the location of the peak also scales like this, what would happen if I have multiple particle species, Doppler fields, coupled to my inflaton? After all, if you think of the standard model, the Higgs of the standard model, the only scalar we really know, is coupled to many particle species, not just one. So the natural embedding in preheating, reheating is to think there should be many Doppler species. And now the question is, could I probe the particle couplings through spectroscopic signatures in the gravitational wave background? That's what I'm going to address now. So, For a single Doppler field, chi1, with a given choice of coupling, G1, I get this kind of single bump. If I now take a second Doppler field, chi2, in a separate universe, separate simulation, single Doppler field with a different coupling, much smaller, because it's smaller, I get a smaller background of gravitational waves at a higher frequency. Now the question is, what am I gonna get when I put the two guys together, coupled to the inflaton? Any guesses? It's almost kind of obvious. You are gonna get something like this, a double peak structure in the spectrum of gravitational waves, which is inheriting the location, not the height, but the location of the original single Doppler field spectra. Due to energy conservation, obviously I cannot maintain the same height, because the energy has to be split now between the two Doppler species, but still you inherit the structure. So guys, this deserves a monkey, clearly, you know. What I'm saying here is that now we are inducing as spectroscopic signatures the information of the couplings in the spectral shape of the gravitational wave background. And of course, this can be generalized to whatever number of couplings you want to consider. In this example 3, I don't do more just because they don't fit in my lattice simulation, but the idea repeats, no? If I have 3 different couplings, look what I obtain, a 3-peak signature, like kind of a stairway, that corresponds to the location of the peaks, to the location predicted, which are these vertical lines, by the single preheat Doppler field scenarios. Good. So, this we call it a stairway signature. We wanted to call the paper Stairway to Heaven, but the editors, you know, don't have the same humor as I do, apparently, and didn't let me go through. Well, let's try to do now a realistic reconstruction at LISA. As I said, I'm shifting by hand these templates that I obtained from my lattice simulations. I'm putting them at low frequency profiles, like if they were a target for LISA. I injected like a double peak structure, for simplicity let me consider double peak, within the noise of LISA, in my LISA simulator. And well, some colors are the injected signal, the other one is the reconstruction. You cannot see them well because they are on top of each other. In other words, the reconstruction is really fantastic. So if I had a signature of this kind for LISA, and I only cheated here in the position of the spectrum, not in the height. The height was naturally coming from my simulation. So essentially, if I had something like this at LISA frequencies, then I could reconstruct the peaks to better than 1%, which means I can reconstruct the couplings at better than 1%, okay? So here is an example where you inject a given coupling theoretical level, and this is the reconstruction in LISA, and at BBO, if in case BBO, which is called Big Bang Observatory, it's a next generation to LISA, which only exists in paper so far. This is the reconstruction. So you see, the accuracy is maybe not the best, but you still get a reconstruction, which is the whole point of this exercise. What I'm showing you here is that it's totally possible to think of using gravitational waves as a tool to prove particle physics, in particular interactions, similarly as we do in the LHC, to some extent. Good, so our example is just a proof of principle, because as said, these backgrounds correspond only to high frequency systems, but it shows you the possibility of using particle physics interactions or gravitational waves to prove particle physics interactions. Okay, and the example shows very clearly that reconstruction is possible. Ideally, what we want is multi-peak stairway signatures in low-scale preheating. This is what I don't manage to engineer yet, but of course, nothing prevents me from thinking I'm going to have a similar effect at phase transitions. And I'm not going to show you that later, but I am truly convinced that I'm going to have a similar effect in phase transitions. And the advantage of phase transitions is that I can lower my frequency to arbitrary frequencies, actually. Because phase transitions, contrary to non-perturbative preheating effects, they have no problem whatsoever to manifest themselves at arbitrary energy scales. So if I have a phase transition at way lower scale than GATT, say at the electroweak phase transition, then I can have a sizable signal at low frequencies, And I'm guessing that in a multi-particle state system, like the ones I'm describing, I would have a multi-stairway signature. Okay. But it's a speculation. Good. Another solution would be, okay, somebody experimentally should design a good detector on high frequencies, and then we could really start for these backgrounds to start probing reheating. Yes?
Why is it so difficult to build a high frequency?
Yeah, because even though I was describing the signal in terms of omega gravitational waves, what the experiment really measured is the strain, which is, if you want, the amplitude itself of the wave. No? In the language of interferometry, it is the relative change of distance compared to the actual length of the interferometer. And in LIGO Virgo, they are at 10 to minus 23. All right? But the higher you go to frequency, to sustain the same omega gravitational wave signal, you need to have smaller and smaller. It scales inversely proportional to the frequency. So if I go to gigahertz, then I need a strain of 10 to minus 30. And this is super problematic because there are all kinds of quantum effects that are going to shield, quantum noises there that are going to shield the possibility of isolating such a small effect. And this is the difficulty. People have thought multiple ideas, but they are far away from having a sensitivity close to anything remotely physically appealing. Yeah. More questions? No? Good. 9:40. Okay, let's continue 5-10 minutes more. So, reheating standard, I just showed you that the standard non-perturbative effects of reheating, which are the so-called preheating ones, can give naturally a very sizable gravitational wave signal, but these are naturally always doomed to be within high frequency regime, unfortunately. Okay, so far. Gravitational waves from phase transitions now, because we've covered preheating. I covered 2 paradigmatic examples. Other examples are just varieties of this, essentially, but they always suffer from the same problem. Gravitational waves from phase transitions. Let me start, and then we take a small break. Now, we saw that reheating, preheating produces this large gravitational wave background, but now we know that the end stage of reheating is a thermal universe. So now I've produced this out of equilibrium distribution of fields, and through interactions with other field species or among themselves, they are going to equilibrate, thermalize eventually in a longer time scale, and they lead to a thermal universe. Good. So we are going to speculate with having a so-called first order phase transitions in this thermal universe. And we're going to see that they also produce large gravitational waves. However, before I go thermal, in reality, I noticed to you before, if you remember, that this hybrid preheating example, the one between Higgs coupled to an inflaton, where I had a tachyonic instability, was also a phase transition. So before I really go into thermal phase transitions, let me embed now, still within the reheating context, this preheating scenario within phase transitions. I hope this is something different that what Oliver told you about phase transitions, because I guess he focused on thermal ones, not sure, but in any case, let me tell you the details in this case. So before going thermal, let's continue preheating, yet now we are in phase transitions. Okay, and that's because phase transition is not just something of the thermal environment, it's not of the thermal universe only. Phase transition is whenever I have a phase transition, and that can be the end of inflation, as I'm just about to show you. Good, so if we continue in reheating, preheating picture, what we saw was a scalar case, and now in order to do the phase transition in a more realistic embedding, let me even gauge the symmetry, and now I'm going to show you what gauge preheating is, and realizing a phase transition at the same time. So we go back to now our favorite model, which is this hybrid model, which has the inflaton slowly rolling in its flat direction during inflation, and the Higgs-like guy, which is coupled to the inflaton in this way. Okay, this is the same coupling. Remember, there is a mass scale associated to the Higgs. is the standard mass scale that it will take the Higgs once you break the symmetry, and there is a critical value. Good, this is the pictorial picture, this is the Higgs direction, this is the inflaton, this is the Higgs direction in 1D. I could have the Higgs as a, whatever, as a doublet with 4 components, and then I would have to do a 5-dimensional plot of this, which I cannot do. Okay, what I want you to picture is this is just one direction of the Higgs. In reality, there can be a more complicated vacuum manifold because the Higgs might have multiple components, but the idea is the same. So my inflaton is slowly rolling here, hits the critical point, this triggers tachyonic mass for the Higgs field, and well, effectively, this is what's going on. This is why I have the tachyonic mass, because for supercritical values of the inflaton, there was a single minimum for the Higgs potential, was this. But when I when I get to the critical value, then it just flattens out, this minimum, and then as I go subcritical with the inflaton, the Higgs starts developing to minima. It has a degenerate vacua, and as I said before, if this was like a doublet with 4 components, or a complex field, sorry, with 2 components, then these 2 minima, instead of being 2 values, would be a circle here. Yes? So essentially what you see is that the effective potential that the Higgs perceives here is evolving in time due to interactions with another field. The standard picture that probably you are more familiar with is to see effective potential in a thermal environment. Due to thermal corrections, the potential also evolves. Here is through interactions with another field. So it is a phase transition. And now I'm going to trigger, once I get here, a tachyonic instability, because the curvature of this is negative. This is the tachyonic mode, and this triggers the growth of my Higgs towards the true vacuum, here normalized to 1. As I grow tachyonically, eventually once I get here, the self-interactions of the Higgs itself are going to screen the tachyonic mass, and then I'm going to recover, once again, a positive defined square mass. So this is a standard Higgs mechanism, where I'm triggering the breaking of the symmetry through this tachyonic instability due to the interactions with the inflaton, and my effective mass goes from positive, negative, to positive here. Then I have a radial mode and a goldstone, or goldstones. All right, it's pretty much the same as always. But now I'm going to complicate it a little bit more, like taking inspiration from a standard model. And just to confuse you a little bit, the notation of this, now I flip the name of variables, but well, I hope this is irrelevant. Now chi is the inflaton, and capital phi is the Higgs, and this is the modulus actually of it. So you can think of the Higgs now as a complex field or as a doublet with 4 components, no problem. Oh, in this example, it's a complex field because I have only a billion Ks, so you could have thought of non-abelian as well. So now we gauge the symmetry, we introduce our gauge field propagation through kinetic term, gauge covariant derivatives, so the interaction between the gauge field and the Higgs, then we have the inflaton, and then we have the interactions between the inflaton and the Higgs. Good, so let's review this phase transition. I came here, I triggered the phase transition, the Higgs spontaneously breaks its symmetry from 0 to a non-zero BEF here. And now there are gauge fields. So if you excite the Higgs through this tachyonic instability, you are naturally going to excite also the gauge fields, because the gauge fields are coupled to the Higgs. This is called a dragging effect. So if I get fluctuations of the Higgs very large, the fluctuations are going to drag the gauge field excitation. And they are going to get very excited, actually. Maybe let's take 2 minutes break, and then we continue with this system. So, we were here with a gauge system where I have a Higgs-like guy. It's an abelian Higgs. Now let's solve the dynamics of this guy to represent the phase transition. And it's enough to do it in Minkowski because even for Gatte scale, the rate of the phase transition is much faster than the actual expansion of the universe. And of course, if my energy scale is even lower, then even more true that I'm in Minkowski de facto, effectively, during the phase transition itself. Okay, so we did this in Minkowski. We choose temporal gauge, and these are the dynamics. You have to solve the propagation of the Higgs. There is also the propagation of the inflaton. There is the propagation of the gauge fields sourced by the Higgs. This is the dragging effect. And there is the Gauss constraint that you need to fulfill due to gauge invariance. The equations of motion, at the same time, we need to solve for the gravitational waves, are our favorite equation, wave equation, sourced by the transverse traceless part of now the anisotropic stress that now has inflaton contributions, Higgs gauge contributions, pure gauge contributions through electric and magnetic field forms. So I'm gonna develop a nonlinear dynamics of all these guys. I'm gonna build up this object, take the transverse traceless part, plug it here, and see what are my gravitational waves. Good, I have three different terms now, covariant, magnetic, electric, plus the standard one that we've been seeing so far since yesterday. This is how it looks. This is the picture of the actual phase transition now in 3D in space. These bubbles represent these bump configurations I was showing you before, now in 3D, and the color coding tells me how close I am to the true BEV. So once I get to 1, I am around the true vacuum expectation value, the true BEV. But initially, of course, you are very far away, that's why you are all in blue, and then at most in the red, the center of these structures, you are getting close. Why? Because this is where the biggest random kicks of the tachyonic instability took over. This is a realization. If I run another realization, I will get the bubbles in different locations. Because I'm getting, this is a quantum effect, the nucleation of these structures. You have quantum vacuum fluctuations, that's the key point, there are fluctuations. Okay, so random sampling of these fluctuations. And then they become tachyonic. Some of them will have a bigger amplitude in some places than in others. And the result is this nucleation of structures. Now, these structures grow both in size, so the width of them, but also in amplitude inside. Look that here I've changed an order of magnitude now, the color coding. So inside this Higgs structure, let me call them bubbles for analogy to a standard thermal phase transitions, the Higgs is getting closer and closer to the true BEV through rolling its potential. That's the tachyonic instability. I get to a point eventually where you see inside the structure, the Higgs is pretty much around the BEV. Look that I overshoot over 1. Why? Because of course, contrary to a textbooks, when you see the Higgs mechanism, the Higgs doesn't just go and sits down there at 1. Okay? This is a dynamical process, so the Higgs is gonna go there, go over, come back, oscillate, and do all kind of nonlinear interactions. That's what you are seeing here, the realization of this. So these are these bubbles when they've already grown to a size that they're about to collide with themselves. And here they are literally colliding in the moment of colliding, but I want to pick your attention, look at the scale here, almost everywhere in the universe, I'm in the true BEV. But look at the scale, sorry, at the picture, maybe it's a bit difficult. Carlos, sorry, can we finally switch off these lights? Maybe better, I think. So look that in between these bubbles, I have some kind of elongated structures. They are not very visible yet there, but they are going to become very visible now in a moment. Let's look at the, instead of, thank you, to the phase transition from the point of view of the Higgs, let's look now from the gauge fields point of view. So this is the magnetic energy density that I'm representing here. Initially, I have this bubble structure as well. This is the dragging excitation of the gauge field due to the fact that the Higgs is being excited. As the bubbles of the Higgs develop themselves, the magnetic field, however, look what it's doing. It's developing these elongated structures, which here are very clear. What are these? These are cosmic strings. I'm actually showing you a realization of how cosmic strings are formed. We'll cover this in the last lecture, which will be after the coffee break. Okay, so let me not dwell with this now, but just to anticipate that, you see, as a possible consequence of a phase transition, I can have some very beautiful objects called cosmic defects, and this is an example of cosmic strings, which actually are very relevant in beyond the standard model physics, because we are really aiming to observe these guys. Let me forget about them. Yeah. So, look at the spectra. These are the spectra of the Higgs. It has a typical middle peak. It might have an infrared peak. This depends on the choice of interactions and hypotheses. So maybe you forget about this infrared peak, center on the idea that there is a middle peak, and then look at the spectrum of the gauge field. This is the spectrum of magnetic field. It has its own peak, and it is a different scale than the Higgs peak. So now the gauge field, actually the spectrum of the magnetic field, the location of its peak in reality depends on the choice of gauge coupling. Given a self-coupling of the Higgs, if I take different ratios of the gauge, so for a fixed self-coupling of the Higgs, whatever value, say 0.1, take different gauge couplings, and then the location, it's depending on this gauge coupling. So again, I'm showing you the fact that the spectrum, of course, of the gauge field excitation, obviously is going to depend on the choice of a strength of its gauge interaction with the Higgs field. That's what this is showing. So what about the gravitational wave spectrum? Well, the gravitational wave spectrum now is going to inherit the peak structure of the matter fields that are sourcing the gravitational waves. I'm going to have, imagine I have the gauge coupling over self-coupling of order 10, then I have my UV peak of the gauge couplings inducing their own production of gravitational waves here. And at the same time I have my Higgs fluctuations inducing their own gravitational waves here. As I tweak the value of the gauge coupling in different simulations to smaller and smaller, and I make it equal to the self-coupling, I superimpose these peaks, which I displace like that, until I have them on top of each other. So essentially, again, now I have two couplings at play, the self-coupling of the Higgs and the gauge coupling, and again I have a situation where I can do a spectroscopy of couplings. And now it's a scalar sector and gauge sector. So my gravitational waves is inheriting the properties of the interactions I'm assuming. And you see, depending on the strength of these interactions, you either have a double peak structure or a single peak. Good? Several peaks, particle physics spectroscopy. This is why I think in phase transitions, in the thermal ones that I can place at any energy scale, I'm going to have a similar effect. Once you plug in the gauge fields, which surprisingly nobody has done yet. Not surprisingly, because it's very difficult to do it in the lattice, but in reality, any realistic system should really incorporate the gauge fields. So what do I get? Multiple peaks at very high amplitudes. But again, I am in a system, remember, that is at high frequency. Because this scenario is at high frequency. If this scenario, I tweak it to a low energy scale, I can do it. Then the problem is I don't get sufficiently high gravitational waves at the right frequencies. The same physics goes on, but then the production of gravity waves is absolutely negligible and then irrelevant from observational point of view. Okay? So the key point, I think, is still to find in preheating some scenario where I can have non-perturbative effects with multiple particle species, let them be in a scalar or gauge, at arbitrary low energy scale such that I can have a sizable gravitational wave production. And that's what I'm not managing to find without fine-tuning of parameters. Yeah. Well, that's saying the same. Could I have, instead of gauge preheating, fermion preheating? Well, actually you do, and you do produce a lot of gravitational waves as well. Fermion preheating, of course, is very special because fermions are fermions, intrinsically quantum fields. There is no classical limit to fermions, so I cannot have parametric resonance because their occupation number cannot grow exponentially. But I can pump energy more and more into UV modes, and that's going to give rise to a very out of equilibrium distribution of fermions, which also produce a lot of gravitational waves, not as much as the bosonic sectors, but it does produce still a sizable, in certain scenarios, signal. But time is finite. I leave you with two references if you are interested. And more interestingly would be that we embed the whole thing that we are discussing into the standard model. You know, or considering anisotropies also of this gravitational wave background. All of these things are open, guys. You know, are problems that we have explored to some extent, depending on a choice of context, okay, very specific context, that of Higgs inflation. But all these problems are open in a general manner, And it's where research in reheating, preheating should really go, into embedding with realistic gauge systems. Good. Reheating, I think, is well covered by now. Phase transitions, we've seen that before going thermal, we can also have a phase transition, actually in vacuum, at the end of inflation, is the example I just showed you. Now let's go thermal. We know that at the end of reheating, the universe thermalizes, and within this context, we are going to speculate with a thermal phase transition. Let me see. Okay, good. So, thermal phase transition, normally, no, I don't know what this is doing here, sorry. Oops, yeah. Let's continue with thermal phase transition, first order, we will see in a moment what that is. I'm gonna build, of course, on the idea that I know that you've been exposed to 4 lectures, I believe, on phase transitions. So I hope all kind of formalism was given to you, including for gravitational waves. So I'm going to give you just an overview of the idea of how gravitational waves really emerge in first order phase transition in the thermal context. Nowadays is one of the topics of major interest in gravitational wave background community because it naturally links gravitational waves with particle physics. It's a topic by itself in its full complexity, so deep that it will take maybe 4 lectures to cover it in detail, and I'm just going to give you a 20 minutes overview on the gravitational wave side here, counting also on the fact that I hope Oliver gave you some deeper view. So, the idea is that once you are in the thermal universe, you can think of a Higgs sector. This could be Higgs of the Standard Model, this could be Higgs of beyond the Standard Model. It's coupled to the thermal plasma, and it has its own potential plus thermal corrections. And the thermal corrections are going to depend on time because they depend on the temperature, and the temperature is like a clock in time. So the temperature is decreasing as time goes by. So as the temperature decreases, then the effective potential that initially had a single minimum is such that it might reach a critical temperature where you develop like a plateau here, and then you start developing a second minimum, which eventually might become deeper than the first one. Now, depending on the microphysics scenario you choose, you can really go, you are going to want to go to minimize your energy here, and you can go through fluctuations or through quantum tunneling. It really depends on the choice of the microphysics. But either way is fine. Okay, very often I see people put this potential and they immediately think that you have to tunnel. This is not true by default. I already showed you an example where instead of arriving to my new minimum through tunneling, we went through fluctuations. They were not thermal, they were induced by the interactions with a field. But with thermal interactions, it's pretty much the same idea. Okay, so either way, you tunnel or you fluctuate, you are going to want to go, your system is going to want to minimize its energy and will go to the true vacuum expectation value. And in doing this, you are going to nucleate or produce bubbles. These are, you see, it's the same concept I was showing you before of these structures, but now in a more cartoonish manner where you have these bubbles. In the case of nucleation, they are expected to be exactly spherical, with maybe some fluctuations, but in principle exactly spherical. And eventually these bubbles grow because they are unstable and they are going to collide. And if this looks very cartoonish, this is a real simulation of spherically nucleated bubbles by my Finnish colleagues, the Helsinki group, where they place a number of bubbles, sampling the nucleation rate computed in a given scenario. The bubbles are unstable and grow and start colliding, and eventually they fill up the whole universe. Okay, it's not really shown there, but they are going to fill up the whole universe in the true vacuum expectation value, which is what is inside the bubbles. Good, so what is the source of gravitational waves in all this complex process? Well, the collision of bubbles, obviously. That's the first source to think of. And that's the first source that people consider for 15, 20 years. It was only very recently, or at least recently in my time span as a researcher, that people started considering beyond the bubble walls. Okay, when I started my PhD, there were only bubble walls collision. But then people realize that, of course, if you are coupled to a plasma, you are going to induce pressure waves into the plasma. These are called sound waves. And of course, if this plasma, due to these pressure waves, develops turbulence, that's going to have its own non-dynamics in the fluid dynamics, you know. Plus, if there are gauge fields involved, in the form of magnetic fields, then there are going to be all kind of magneto-hydrodynamical effects involved in the game. And this is why this is so complicated, because we have changed the picture from the simple modeling of just the Higgs sector to now the Higgs sector coupled to a fluid of relativistic species which have its own hydrodynamical evolution, which is very nonlinear physics, and then with possible magneto-hydrodynamical effects. Okay, this is what's making this all very difficult, and this was only first realized starting in 2011. Okay, so very recent. I was in Helsinki as a postdoc when some of these people started working on this. So, collisions of bubble walls, sound waves, and MHD effects, magneto-hydrodynamical effects. This is the three sources typically that people consider in a complex process of phase transition in the thermal environment. There is an environment, okay? You need the fluid. This is the difference maybe compared to what I was showing you before. Technically, this means to follow again the gradients. So now you need to follow the gradient profile of your bubbles. You need to follow the relativistic dynamics of your fluid and have a scalar fluid coupling. And you need to follow your gauge fields and have a coupling between them and the fluid. So it is a bit complicated and is going fully numerical nowadays. Let me give you a hint or a picture, a flavor of this. Sound waves, essentially, it comes from the fact that I have my bubbles. In blue there is the fluid. The bubbles all collide among themselves, but also are stirring up the plasma. And then by heating the plasma as they expand and they collide, they are going to create these sound waves. The sound waves are nothing but waves of pressure. And these waves of pressure actually are going to sustain themselves for very long. Again, this depends on the properties of the plasma. And these waves themselves are going to produce a lot of gravitational waves. And then, as I said, if there are magneto-hydrodynamical effects or possible turbulent effects, now you need to take that into account in your fluid dynamics, and people are starting to address this, but you see the archive numbers. These are the first papers addressing this numerically for the first time. So, in summary, this is an open problem, how to really model as good as possible these signals before an apparatus like LISA flies. Okay, because we need to take under control this production, and that's not easy at all. And you will see in a moment why I'm talking about LISA. So let me put now some formula together. This is a causal production of gravitational waves. So the frequency or the typical mode of excitation is going to be sub-Hubble, which means if I parameterize it like this, epsilon is smaller than 1. Okay, if epsilon is 10 to minus 2, this is like having a 10 to the 2 factor here instead of 1 over this. And this means that I'm 2 orders of magnitude inside my Hubble radius. Good. The Hubble rate is determined by the temperature at which the phase transition takes place. The frequency today is the frequency at the time of the phase transition times the redshifting factor. And this in the thermal universe environment is very easy to redshift now. I know everything. I redshift till today because I'm assuming radiation in the thermal environment, and then I go all the way till today. And this is the master formula once you use your Friedman equations. Essentially, the frequency today is of the order of 10 to minus 5 for a TeV scale of temperature. 10 to minus 5 in Hertz, sorry. And why is that relevant? This is millihertz, if you want. This is relevant because for this energy scale, which is the electroweak scale, around the electroweak scale, these are the LISA frequencies. So essentially, LISA apparatus, the will be first laser interferometer in space to detect gravitational waves. By chance, it turns out that it's a natural proof of the electroweak symmetry breaking, of a phase transition driving the electroweak symmetry breaking, as long as that symmetry breaking is embedded into beyond the standard model so that we have a first order phase transition. Otherwise, in the standard model, it's a crossover, which means it's a smooth transition to the true BEV, and then you break the symmetry the same, but you don't produce gravitational waves. Okay? I really need embedding in beyond the standard model. And this is why so many particle physicists are interested in this, because by starting this process, embeddings, different embeddings in beyond the standard model, you could prove the different physics of these embeddings, presumably. Okay? That's the idea. Good, for that we really need to know this parameter, and of course that parameter depends on the microphysics. So, gravitational wave generation, of course, depends on the bubble properties, and the bubble properties are what are going to tell me what this epsilon parameter is. Essentially, a relevant parameter is the duration of the phase transition. I nucleate the bubbles. Depending on the properties of my choice of model, these bubbles will have already one size or another. The rate of nucleation will be one or another, and they will encounter themselves at a given time scale. This is the beta minus 1. And of course, they are going to propagate with a given velocity, these walls, and that velocity depends on the interaction with the plasma. So it can reach a terminal velocity, or it can have a time-dependent profile velocity until they collide. Again, depends on your choice of interactions. There is, of course, a natural length scale, which is the size of the bubbles upon collision. And obviously, that scale has to be there in my spectrum of gravitational waves, because in the moment they collide is when they start producing gravitational waves. So essentially, epsilon is actually given by either the time scale, parameterized by the Hubble time, so this is the inverse of these two guys, or the length of the radius at the time of collision of the bubbles that gets imprinted as a scale in the fluid dynamics in some waves, and then it gets inherited there with some redshifting. But altogether, you see, these are the fundamental scales that are at play here. There is nothing else. The frequency today, as we said, is this master formula with the epsilon parameter telling me how sub-Hubble I am at the time of the collision of the bubbles. And essentially, there are three parameters to play: the time duration, the velocity of the bubbles, which can be a complicated profile, and the temperature of nucleation of the bubbles, or of collision, if you want. Yeah. The amplitude today is very easy to do a scaling argument that it should really go as the square of the energy density of the source, which for the bubble collisions is just the energy in the bubble walls. And this ratio, you can write it like this, as this parameterized formula, which contains the fraction of energy of the vacuum configuration to the environment outside, and the fraction of the kinetic energy of the wall to the vacuum energy density. These two ratios characterize completely this other ratio, and this tells me the amplitude today modulo redshifting factors, which are these. Okay. I'm not showing you how to do that, but it's actually a simple exercise. You can have a look in my review with Chiara Caprini, for instance, if you want to see the details. Let's do some numbers. Omega radiation is suppressed today as the order of 10 to minus 4. A typical epsilon in a good, very strong first order phase transition is of the order of 10 to minus 2. And this ratio, let me speculate, let's put 10 to minus x. So altogether I have 10 to minus 8 here times to 10 to minus x. The question is how small can I tolerate this? And typical values that you get altogether is 10 to minus 10, 10 to minus 13 for today's amplitude. Of course, when I say typical, it means the values we are demanding to our microphysics to have an observable signal. It's not guaranteed at all that I have a first order phase transition and it gives me a signal observable. If it's not strong enough, then it's not going to give me a ratio strong enough here. Okay? Good. This is not the most general modeling. The most general modeling requires nowadays to do fits to hydrodynamical effects and turbulent effects, which you have to treat with the full MHD coupled to a scalar field simulations. So that's the part I'm skipping the details. I'm just going to show you the results. I hope Oliver showed you a bit of that. Is that the case? No. They say no here. Yes, they say yes there. Okay. So at the end of the day, guys, you know, you see, you have a complicated process which is nonlinear, but of course you are going to have a typical parameterization of your amplitude of the background today as a function of your key parameters, which are the ones I'm describing here. And the frequency is also going to be a function of these parameters. And just calibrating those formulas is the game that people are playing with this kind of numerical simulations nowadays. Good, which are very difficult simulations. This is why so few people have jumped into them. Now, typical example from collision, sound waves, and turbulence. So I have a contribution on gravitational wave spectrum versus frequency today of MHD, which is subdominant in this case. And then I have a contribution from sound waves in green and from wall collision in blue. And in this case, the sound waves dominate a bit in this frequency range, so I inherit a double two-peak structure. Again, how you play with your parameters of the phase transition or of your microphysical model, you will get single peak, two peaks, or even more complicated structures. The relevant aspect here is not so much that you understand this peak comes from bubble collisions, this other comes from fluid-related processes, is that an apparatus like LISA, an experiment like LISA, could potentially detect this background. This is the message I think you should really take from here. Why is this relevant? Because of what I said before. We could be probing literally the electroweak symmetry breaking of the universe in the early universe, and hence possible embeddings into beyond the standard model physics. Okay. Good. Bubble collisions, the game, it was played when I was your age analytically, then eventually it went fully numerical. Sound waves, it started fully numerical from the beginning. It remains fully numerical, but of course people have done some hints of analytics, but at the end of the day, if you want to have this under control, you need to go to the lattice. MHD turbulence started analytically, but that was very hand-wavy, and then eventually people jump into the actual numerical thing, and it turns out that it's extremely complicated and it's far away from being settled down what is the real physics going on there. Okay? All of these are open problems. Because LISA is sensitive to this range of scale, this corresponds to the range of frequencies of LISA. LISA can probe, we've said it repeatedly, electroweak phase transition embeddings in beyond the standard model. This could be what you get in single extensions. So you add an extra scalar field, like in MSSM, for instance, direct coupling to Higgs to other scalars. You can have extra couplings to other sectors, or non-renormalizable higher dimensional operators, which comes from integrating out whatever physics that you don't know about it at your scale in the LHC, for instance, but you are still left, at the electroweak scale, sorry, but you are still left with higher dimensional effective operators. These are ways in which you can promote the electroweak symmetry breaking of the standard model into an actual first order phase transition. And also you can go beyond the electroweak phase transition. You shouldn't only focus on that. You could think of dark sectors, which maybe have their own phase transition, providing a dark matter candidate, or even more imaginative, using extra dimensions. You can also think of phase transitions within the extra dimensions. And since everything gravitates, from the point of view of detecting the signal, I don't care what's the origin of this. I detect a gravitational radiation. Okay? Good. So this signal is putting the interplay between cosmology and particle physics, and it might have also deep connections with baryon asymmetry and dark matter. However, typically in the direction in which you do baryogenesis here, you actually don't produce large gravitational waves, and vice versa, unfortunately. But it is possible to tune your models. Gravitational waves are clearly a new proof of beyond the standard physics. This is a paradigmatic example, and are complementary in this way to particle colliders. But of course they are limited. The LHC is of course putting pressure into these beyond the standard model scenarios. And eventually when LISA flies, we will see what's the parameter space available for some of these scenarios to produce an observable signal, maybe none. So, can we really detect a first order phase transition? Well, LISA or Einstein telescope can, definitely. But LHC is going to be putting pressure in some of these scenarios, particularly for the electroweak phase transition. Assuming we focus in the ones that are not ruled out by LHC, LISA and Einstein telescope can definitely put constraints, very strong constraints, in this parameter space. But the predictions depend on many assumptions, particularly in sound waves, which are the dominant source in most cases. So a very relevant question, is our modeling correct? And this is, I think, where the next 10 years is going to be the game played in predictions of gravitational wave backgrounds from phase transitions. We are going to have to understand the fine details of our modeling of the nonlinear physics of these simulations, which, as I said, are pretty hard. And also, a sad thing is that even if we detect one of these signals, which at the end is a single bump or two bumps, you get alpha, beta, and the energy scale. And then there are a plethora of BSM models that could do the same. So how are you going to distinguish one model from another? It's not clear that from a single detection of a spectrum, we are going to be able to really tell apart between one BSM scenario or another. Certainly, we will rule out certain families, but we will keep entire families of models. Good, so that's for my summary of phase transitions in the thermal environment. With this, I've covered the fourth topic, the third one in the core topics, and we will go into cosmic defects in the fourth and final lecture, which will be after the coffee break. I believe we still have 5 minutes, or 3 minutes. If you want to ask any questions before the coffee break, go ahead.
Any questions for that? Okay, thank you for the lecture and the report.
Welcome back. So this morning we have double session because I have to leave after lunch, and the other speaker was kind enough to exchange. I hope you were aware. Sorry about it because it's a bit of gravitational waves in the morning, but that's what it is. So we go to our fourth and last lecture, which, you know, the beginning of which was supposed to do the thermal phase transition, which I already did, because I want to cover also a bit of the astrophysics. So we left it here. Good? Now, let's go to our last topic of early universe sources, the one of cosmic defects, which I assume is maybe the one you are least familiar with, because not always topological defects are studied in your master courses. Actually, I never studied them in my master courses. I had to learn that by myself as a researcher. So what we've covered is phase transitions, either in vacuum, for instance, ending inflation, or in thermal environment. They are very interesting sources of gravitational waves. And in the thermal case, I could think of placing a signal at arbitrary frequencies just by thinking of a phase transition at arbitrary temperatures. Good. But a natural consequence, which is not always guaranteed, but is certainly very beautiful consequence in certain cases, is that if I have a phase transition, I may have cosmic defects. And cosmic defects are very energetic configurations that produce two types of gravitational waves, the irreducible background, I will refer to it like this, like the one is guaranteed by default, and in the case of strings, we'll see that there is an extra production coming from loops, which is actually very interesting and very important. So cosmic defects are still in a sense part of phase transitions because they are a possible consequence of them. And let's have a look into the actual physics of cosmic defects before we discuss gravitational waves. So cosmic defects are a possible aftermath product of a phase transition. It was Tom Keeble, the great genius of Tom Keeble, that pioneered the study of topological defects in the early universe. I personally find extremely unfair that he didn't get the Nobel Prize for the Higgs mechanism, because topological defects is nothing but a consequence of the Higgs mechanism. And it was not Higgs or Engler or any other one of the 6 famous people other than Keeble who really generalized to non-abelian theories, and that's what Steven Weinberg took as an inspiration to build the SU2 cross U1 standard model symmetry breaking. Okay, so, and this is declared by Steven Weinberg and also by Higgs himself. Because, you know, the papers that were awarded the Nobel Prize were very simplifications of the real thing, and the more complex aspect actually were only understood by Keeble and were pushed forward by Keeble. And then Steven Weinberg really built on that in order to do the standard model. Yet, you know, Keeble passed away, unfortunately, a few years ago, but he was alive when they awarded the Nobel Prize. They were actually all waiting in Imperial College, you know, to announce the Nobel Prize winning of Tom Keeble, and you can imagine their faces, you know, when they didn't give it to him, you know. And all of this is because of this stupid rule that Nobel Prize can only be given to 3 people. And since Tom Keeble signed his paper of the Higgs mechanism with 2 other guys, then they should have given the Nobel Prize to 5 people, and because of that, they left them out, you know. So it's really stupid and really unfair, honestly. Good. Keeble, in '76, so years after they have proposed the Higgs mechanism, he realized that a natural consequence of a spontaneous symmetry breaking is not only that you can give masses to particles and so on, there is something else, which is the following. Think of a group of symmetry G, which you spontaneously break to H, a smaller group, then you automatically form what we call a vacuum manifold. You should think of this like the space, the manifold, formed by the broken generators. Essentially, there's going to be a set of degenerate vacua where your Higgs field, represented by this vector, can take a position. But if this is the case, in the early universe, I have a spontaneous symmetry breaking. In one region, the arrows within the internal vacuum manifold are going to point in one direction, in another region, in another, in another region, in another, and so on, so forth. And of course, regions are causally disconnected. So it's impossible that the arrows are connected everywhere causally, you know, in the same direction. I'm necessarily going to have domains of this kind in regions of a space where the direction within the Higgs vacuum manifold is different. And now the question that Higgs realized, what happens in between these regions? What happens here? It turns out that what happens there depends on the topological, so-called topological properties of this vacuum manifold. Topological properties are a way of classifying the topology of these spaces, and this is done with the homotopy groups. And whenever one of these groups is different than trivial, than identity, then you are going to have these funny objects, which are called topological defects, emerging. So let's look at an example of this. And now, very important, I want you to realize that whenever I have a phase transition, whether I have topological defects or not, this doesn't depend on whether my phase transition is first order, second order, crossover, or whatever you want. It also doesn't depend on whether it's thermal or it's through field interactions, as I show you in the lectures. It only depends in the topological properties of the vacuum manifold. So if I have a spontaneous symmetry breaking from single minimum to a degenerate set of vacua in the true vacuum, now take a two-dimensional slice of the universe, x, y position, and imagine this process in different corners, different regions in space. Within the internal vacuum manifold, my Higgs is going to randomly point to different directions, because this is a spontaneous symmetry breaking process. Here, the spontaneous means really random. Now, if that's the case, now bring them together, this vacuum manifold here to the origin, and this means that the Higgs is going to be pointing in different directions in this particular realization. Okay, this is a random realization, but this situation might happen. If that happens, the only possible solution for the continuity of the field is that I have this kind of spherical, circular symmetry here. So essentially, my Higgs field has to be rotating at least 2 pi within its own vacuum manifold. But very importantly, if the strength of the arrow points to the fact that the Higgs has a BEF, a non-zero BEF, necessarily at the center of this configuration, the Higgs has to climb up the top of the hill and then has to be 0. It's the only way to make it continuous, because in any other part, forget about the exact point where it's exactly 0. Anywhere else, it has a non-zero BEF. So the only way to make that continuous is that at the end you go to 0, literally. But if you go to 0 literally, then you pick up all the potential energy of your potential. So essentially, you are going to produce these configurations which are topologically stable. You cannot undo them. And for instance, this is the case of global strings. You see the Higgs circulation I was pointing out is precisely this. And inside here it goes to 0, which means the potential energy goes to a non-zero value. So I have a very energetic configuration. The same goes for monopoles, or the same I could have for so-called non-topological textures if the breaking is of a higher order than SO3. So essentially, as a consequence of a spontaneous symmetry breaking, but depending on the microphysics, so the properties of the vacuum manifold, you might have emerging these structures called topological defects. They can be of various kinds, cosmic strings, there can be domain walls, which are not drawn there, monopoles, or textures. Good, this is one example from my thesis, actually, so some years ago, where you see here how in a phase transition, there emerges these elongated structures. This is the Higgs. The Higgs inside there has a minimum amplitude of the field, maximum potential energy. And you see here in a two-dimensional cut, the Higgs field circulating in its vacuum manifold from 0 to 2 pi. You see, if I were to cut any string, I would encounter this kind of color coding. You see it's the same here. Why? Because I only get the strings wherever I have a non-trivial winding. If I don't have a winding, no topological defect. But if I create a situation in the early universe where randomly windings are created, you cannot undo that. Good? What about gauge fields? If now I have not just scalar fields, but the scalar fields coupled through some gauge symmetry with gauge fields, now the gauge fields are going to follow the same pattern. And we already saw this picture. Remember, I anticipated before that in the phase transition we were having at the end of inflation, I was showing you cosmic defects. So this is the magnetic field flux, if you want, which are the concentration of energy of the gauge field in the form of magnetic field. There is also electric field to some extent, but mostly magnetic field, along the position of points where the Higgs has a non-trivial winding. Good? Beautiful, right? So, you know, the most beautiful thing is that I saw this emerging in my simulations in my PhD without knowing what topological defects were. I had never studied them, and I was showing that coming out of the simulation. I was like, wow, what the hell, you know? And then, of course, I understood and realized that there is a whole world of people who had studied these guys way before, no? And what they had done is to classify that you can have different types. This has to be, by the way, with the dimensionality of a space-time. We are in 3+1 dimensions. Then we have domain walls, cosmic strings, possible monopoles, and non-topological textures. If I was in a 2+1 dimensions, I could have a different variety of guys. If I was in a n+1 n-dimensional space, I would have a different type. Okay, but since we live in 3+1 dimensions, these are the classification. Independently of the type of topological defects, causality tells me that necessarily there's got to be a correlation length between them, which, or if you want, sorry, microphysics tells me that there has to be a correlation length, a typical scale between them once they are born. And causality tells me that, causality tells me that this scale, of course, cannot be longer than the causal distance at every moment in the universe, which is the Hubble radius. Okay, once I'm in the normal 3 mm Rosen-Walker background metric. And now the great insight of Kibble is that he realized that you may start with a correlation length that is much smaller than Hubble, but eventually, and rather fast, you have to arrive into what he called the scaling regime, such that this fraction, which is the ratio between this length scale and the Hubble radius, it goes to constant and of order 1, which means that the typical distance of the defects is always tracking the causal distance at any moment in the universe. This is the scaling regime. This also means that momentum is naturally normalized to the Hubble scale. This is co-moving momentum, this is co-moving Hubble rate, or I can write it like this, momentum times conformal time. I'm always going to be tracking the Hubble horizon. Of course, there could be violation of this scaling, and we will see some example later on, but let me assume it's exact. Then it means that the distribution, imagine these are cosmic strings coming transverse to the screen, you know, which their own curvature going one way or another, but the typical distance between them, it's always growing with the horizon, essentially. So in a sense, it's a self-similar distribution. If you are in a given arbitrary time of cosmic history, you tell me that time or the energy scale, I tell you the Hubble radius, and hence the typical distance between these guys. And this is why it's said that typically there is one of these guys per horizon when you produce them, okay? Remember, this is obviously a speculation with physics. In the standard model, if I do not embed the electroweak symmetry breaking into beyond the standard model, then I don't produce topological defects. But if you do certain embeddings, then you could easily think of producing topological defects. Or if not, I could think of a BSM independently of a standard model where I have a symmetry breaking pattern, for instance, in grand unified theories, where I have a bunch of symmetry breaking phenomena down to the standard model, then that typically produces, for instance, cosmic strings, and often monopoles. Okay? So it is a matter of what's your symmetry breaking pattern. Now let's imagine we've produced cosmic defects, and let's understand what are the signals produced. Let me start with the irreducible gravitational wave background. Good. If I have defects, they have a lot of energy in the form of gradients of the scalar field. The gradients is in the profile inside the core of the string, a string or monopole or whatever, domain walls. And if they are gauge, they are local, then they're going to have electric and magnetic field configurations as well, which are also extremely localized inside the core of the defects. The size of the core is of the order of the inverse mass scale of the problem. So this is a Higgs mechanism that gives masses, for instance, to the gauge fields, or the Higgs itself has its own mass in the true BEV. The inverse of those mass scales is the microscopic core of this object. So it's really microscopic. All right? But at the same time, this is a macroscopic object because it can extend, for instance, in the case of cosmic strings, to cosmological distances. Now, they have a lot of energy in their cores, and there's going to be a non-trivial transverse traceless part of their energy momentum tensor. This is going to be non-vanishing around the cores. So I can compute the two-point function of these guys. This I call the unequal time correlator, because I'm taking the two-point function at two different times. And the unequal time correlator can only depend on the scale and in the two times. So now let me use a formalism that I haven't shown you in reality for stochastic backgrounds, which is if I know my source and I know its two-point correlator, then I know the energy density spectrum is necessarily given by an integral over cosmic history over this unequal time correlator. This comes because remember our favorite equation, wave equation of the tensor, is equal to the source. But the spectrum of the gravitational waves is quadratic in the tensor mode. So my energy density spectrum has to be quadratic in the source. And this quadratic form is the expectation value of the unequal time correlator of the transverse traceless part of the energy momentum tensor of the defects. All right? So if you know how to predict this, good luck, of course, but if you know how to predict that, you plug it here and you get your answer of the spectrum. Good. This is comoving scale, conformal time. And now let me do the magic of cosmic defects. So if a cosmic defect network, whatever they are, domain walls, monopoles, cosmic strings or whatnot, if they are in a scaling, once they are in a scaling, the two-point function can only depend on a scale in this manner. Because this is what a scaling is. It knows nothing about the actual scale, because it's always tracking the horizon, the inverse of which is the conformal time here. So essentially, this means, let me go back, that this function, that is a function of three variables, in reality can only be a function of two variables in dimensionless combinations kt and kt prime. And for dimensional reasons, I need to pick up here some dimension full parameter or constant, which is the square root of the times. Okay, but this is an implication of a scaling, a mathematical implication. If I'm in a scaling, my unequal time correlator has to behave like this. If that's the case, let me plug it here. And now my question is, what is the energy density spectrum of the gravitational wave background emitted by a network of cosmic defects that is moving in scaling, which means it's moving at relativistic speeds because it's tracking the Hubble radius. So the answer is I plug this form here. Now I take into account what's the expansion of the universe in radiation domination for conformal time. This is linear in time, so 2 powers of time. Take into account that I have here this square root, and there is k to the 3 here. And now the magic happens. Let's introduce the k to the 3 inside this integral, and then voila, the integral is written in terms of a dimensionless form. You see no more the scale, just as a consequence of being in scaling. So essentially this integral is what? A number. It can only be a number. So it's constant. It doesn't depend on a scale or on time anymore. The only scaling in time I have is the standard 1 over a to the 4th due to the fact that gravitational waves are relativistic degrees of freedom. And I'm not inventing anything, I'm just pushing the formalism, and the formalism tells me, that this is the consequence. So, the gravitational wave background from a scaling network of whatever cosmic defects, the spectrum today is going to be what? A scale invariant, with an amplitude suppressed by the energy scale at the formation of the cosmic defects, the BEV, suppressed to the Planck mass to some very strong power, 4, and times this number, which depends on this integral, which depends on the unequal time correlator, which characterizes the type of defects I have. So if I have a type of cosmic defects, I can simulate them and compute them analytically, depends on your skills. You can compute the unequal time correlator in scaling, then you compute this constant, you plug it here, and you get your answer of what is the energy density spectrum of the gravitational waves emitting, just because these guys are in scaling, just because of that, because I have relativistic objects moving in scaling. And this is the same for whatever nature of your phase transition and whatever type of defects, because this has nothing to do with the nature of the defects or the phase transition. It has to do with being in scaling in radiation domination. Be careful. If now I extend my computation to matter domination, I get another integral of this kind over the unequal time correlator during matter domination, but I pick up some scale dependence. Well, it's not very relevant, because now I have a piece that is constant during radiation domination, plus a piece that is scale dependent during matter domination. But matter domination in reality happened very late, very close to the present in a sense, which means that if I plot you this spectra, we have this plateau for all frequencies of interest corresponding to radiation domination, and then we pick up here this k to minus 2 corresponding to the short period between today and equality between matter and radiation. You might think that equality happened a long time ago. It did, but in terms of a scale factor, it didn't happen a long time ago. It happened only a factor 1,000-ish in redshift, which is recent. Okay? Of course, the universe was still in a plasma of particles, okay? But it has only expanded a factor 1,000 ever since, which means that this corresponds to very, very low frequencies, cosmological wavelengths, which I don't really care about. So I do have this plateau prediction, and depending on the BEV, I could have an observable signal or not. However, this was assuming exact scaling. Now, for instance, for the interesting case of global strings, which emerge naturally in dark matter axionic models, you guys already seen this in the lectures in the previous days. You produce global strings, global string networks. People think that there might be log corrections to this scaling, and they have found within the limited range of the simulations, they have found these log corrections, and if you take them literal, you can talk now about log scaling or exact scaling for these global strings. And actually this boosts in the infrared, in the small frequencies, the signal. This is the log correction. So if this is true, then these signals can become really observable now within PTAs or even LISA or other detectors. The problem is that the simulations that show that there is log corrections, of course, as any lattice simulations, they have a limited range. And here we want to simulate the whole range of evolution of the universe. And then they have to extrapolate what they see in the limited range to all cosmological scales. And that's an extrapolation. Other people believe, among them myself, that if we had a bit more of power, computer power, those simulations that show the log scaling eventually will settle down into the normal scaling, which means that you have some growth here, but eventually you are going to go to a plateau, as always. You know. The field is open. The answer is open. This is a hot topic because, of course, this signal can be really used to prove a cosmological action, and in particular cosmological action as dark matter, no? As an interesting candidate of dark matter. The difficulty is that you have to do this fully numerically. I think George was already telling you about this, that you have to do these lattice simulations, and these lattice simulations, contrary to preheating, they are more difficult because now you need to simulate the whole evolution of the universe, which is not possible. So you can only simulate a limited range of scales and then extrapolate or have some argument to predict what happens afterwards. Okay? Good. So good, so far so good, I hope. 1 second. For the idea of irreducible background. So just because I have defects in scaling, which means they are moving very fast and huge concentrations of energy with gradients, they are going to emit gravitational waves. That's this irreducible background.
You mentioned the UTC that we needed to compute this. I may not be recalling it correctly, but did you comment on how to compute it?
Sorry, can you?
Did you comment on how to compute the UTC?
Did I comment me how?
Yeah, did you comment on that?
No, I didn't comment. Yeah. So these ones, for this example, to get numbers here, we use the unequal time correlators in scaling from lattice simulations. Okay, so again, these lattice simulations has certain limitation because the range of scales is only finite, but if we are clever enough with the lattice simulations, we can drive them into a scaling regime. Once you are into a scaling regime, you don't care about the scales anymore. So if we can sustain for a little while the scaling regime, we can extract these unequal time correlators. Yeah.
And there's no way to compute these from first principles?
There is way to compute them analytically. I wouldn't call them from first principles because in the case of strings, you can do very mechanical modeling of the strings like segments that they go rejoining and moving. And there is something called the velocity one scale model that imitates the idea of strings moving, you know, as individual segments. And then you can play around with those analytics to predict the unequal time correlator. But it's not very precise. This is the problem. So ultimately, the way to extract this information, in the case of field theory defects, is really from field theory simulations. In the case of Nambu-Goto simulations, which are infinitely thin strings, is from the Nambu-Goto simulations.
Also for the radiation domination integral, should that be up to x equilibrium or just the 5x?
Until arbitrary x. Arbitrary x, okay? Because the point is x equilibrium, you are right, this would be my upper bound, but way before that I have converged already. And that's why I don't care about the upper bound, and this is a number. This is a number because it becomes insensitive to x. So this is not a function of x, even if I'm writing x here, because this converges. This dies away sufficiently fast such that I die away, I don't compensate anymore at the bigger x values, so I don't need to reach to x equilibrium. But technically speaking, you would be correct. It's just, it's as misleading as putting x as x equilibrium, because in reality, it doesn't depend on the upper bound. That's precisely the point. Yeah. More questions? Okay, if no more questions, I go to the next point, which is in the particular case of cosmic strings, I'm going to have an extra production of gravitational waves on top of the irreducible background that I have just described. Why is that? So, local string networks, let's think of local strings, the ones that are represented by scalar and gauge degrees of freedom. They are assumed to be in exact scaling. And from simulations we get that, and from Nambu-Goto simulations that I will discuss in a moment, which assume infinitely thin strings, we see exact scaling. So, scaling dynamics is assumed to be exact. Now, people think of them in the Nambu-Goto picture. Nambu-Goto picture means that I can think of the defects as being literally aligned as opposed to having a width inversely proportional to the mass scale of the problem. So in reality, these guys have this width, but this width is microscopic, whereas the length is macroscopic. So that's why Nambu-Goto approximation, which neglects this width, it's assumed to be a good approximation. And for the motion of the long strings, this is certainly the case. So we can assume Nambu-Goto picture. Oops. Now, I have now a bunch of strings, very long, infinite actually. I produce in my phase transition these guys, and now they are gonna cross with each other. Why? Because either they self-cross with themselves by accident, or either they cross with another one. Either way, they are gonna chop off loops. So you see, out of the infinite string, you are gonna chop off a loop from its own self-interaction or from the crossing of two strings. Then you are gonna continue here with other infinite strings, but now you have a loop. Good, so the picture of a network of cosmic strings, it's always a superposition of infinite strings and loops. Look that I put infinite in quotation marks, because in reality this depends on the geometry of the universe. If the universe is infinite and flat, as we think the local universe is, then if you extrapolate the local universe ad infinitum, then the strings would be literally infinite. If the universe is close, so imagine there is a radius of curvature, the inverse of which is much longer than the actual Hubble radius today, then the universe would close on itself eventually, and then these strings will also be loops, but just wandering around the whole universe. We don't know that, okay? Because all we can tell is the observable universe, which looks flat, Euclidean, and then if you extrapolate that to ad infinitum, then this would correspond to infinite strings. Either way, they are gonna chop off loops which are sub-horizon scale. So when they produce these loops, they are typically of a given size that is sub-horizon. So loops are formed. Good. What do I do with this? Well, these are huge concentrations of energy in the form of a closed configuration. So what's gonna happen? They are gonna vibrate under their tension. This is like a string, you know, of a guitar, except that it's closed over itself, but it has a lot of energy, so it's gonna vibrate naturally. It has to oscillate. And it has features, such as kinks and cusps, which are discontinuity in the otherwise smooth configuration of the loop. Then you are gonna emit gravitational waves from these features. And now I have a collection of many of these loops. All over cosmic history, I go producing many loops, and I go accumulating them, and they go vibrating. I go producing them in many sizes, and then I'm accumulating a signal coming from the superposition of the so many loops I'm producing. That's gonna give rise to a gravitational wave background from the superposition of all these signals. And this is the gravitational wave background from a cosmic string network based on the loops, not on the scaling on the infinite strings. So a string network is based on a string, infinite strings plus loops. The infinite strings decay into loops, so the loops really are originated from the crossing of the strings, of the long strings, sorry. And the loops are gonna decay, in principle, into gravitational waves. This was the speculation of Vilenkin already 40 years ago, more than 40 years ago. And actually, originally, historically, was the first background of gravitational waves that people were discussing, the one from loops, and not the irreducible one that I was talking about before. Loops decay via gravitational waves. Gravitational waves are actually radiated by each loop in harmonic frequencies, harmonic with respect to the period of oscillation of the loop. And there is a simple formalism that tells you that the power emitted of gravitational waves for each mode, which is a harmonic of the fundamental mode, which is just the inverse of the period, essentially goes in this form. The total power emitted, so the time derivative of the energy emitted by a single loop, it simply depends on the tension of the string. Okay. Where this prefactor gamma is just a numeric factor you adjust depending on the type of loops you get in the simulation. Now, in reality, this is a Nambu-Goto description, where I have my loop oscillating under its tension, and this is correct. Nambu-Goto is capturing that well. But my guy, my loop, is a field theory object. And it has a width. It has really a profile inside the width. And nothing prevents it from decaying into particles. And this is what people have missed for 40 years, I'm afraid. That they have been describing the Nambu-Goto prediction. Nambu-Goto intrinsically doesn't have particles because it's not made of nothing, whereas in reality, Nambu-Goto was a way to describe the dynamics of the strings, but the strings are really made of fields, and I can emit quanta of these guys. Nothing prevents me from doing it, and actually that should happen precisely for the same reason I'm emitting gravitational waves. I have a lot of energy in the loop. So from the kinetic motion of the loop, nothing prevents me from emitting the quanta of these guys. Now, in the following, I'm going to assume the historical path where only gravitational wave dominates, but I anticipate you that actually lattice calculations we are doing very, very recently, they show very clearly that you emit particles, for instance, scalar field modes, radial Higgses, or gauge fields, even if they are massive. And the decay rate of these particles for the realistic loops in a phase transition are way faster than gravitational wave emission, for the simple reason that gravitational wave emission is suppressed due to the weakness of gravity. And this means that this whole picture I'm going to tell you next in reality does not sustain. But I'm going to pretend that's not there, because we haven't published it yet. Hopefully we will put it in the archive next week, actually. So this is how hot this is, how, on real time this research is going. But I'm going to ignore that, and I'm going to stick to the idea that they only emit gravitational waves, which means that their source of decay is only gravitational radiation. And hence I'm going to take into account the rate of gravitational wave radiation to take into account how slowly they decay, they shrink. If that's the case, because the loop oscillates, it's going to emit gravitational waves, as we said, in harmonics. This was done by Vilenkin and then developed by many others over the years. And you should think of it as an extra emission on top of the irreducible background that I already described before. And it's only extra emission for strings, because only strings produce loops. Okay? The strings are the only case where through the crossing I produce an extra object, which are the loops. Good. It's a whole formalism of the energy density of gravitational waves, which is proportional to the tension, and then an integral over all cosmic history with some dilution factor of the loop number density, so the number of loops I have per unit of length, times their length, times the power emitted for each loop, with the corresponding redshifted of the frequencies at the time of emission. Expansion history, I have to integrate over all the cosmic history of the universe over the loop number density predicted, which people take from Nambu-Goto simulations. Okay, so you plug in this from Nambu-Goto simulations. Nambu-Goto simulation has grown to a very good state of the art. They show a scaling of the full network, and they can predict very nicely the loop number density. And then in Nambu-Goto, you can make predictions of what is the specific power emission of a single loop, which typically scales as a power law of this kind, depending on the features you have in the loop. I put all together, and this is the result. If you integrate that for the different moments of history in time, you get a scale invariant background. That's because the loop distribution are in scaling, and we already know that any scaling source gives a plateau in radiation. And then I get these features due to matter domination and later on a tail. This looks very similar, you might think, to the irreducible spectrum I was showing you before, but the difference is the amplitude. It turns out that this mechanism, as taken per se in Nambu-Goto, is much more powerful than the irreducible background, orders of magnitude more powerful. So the amplitude of this signal can be really large. The properties of it, the position of the peak, or the amplitude of the plateau, depends on the microphysics choice. So depending on the loop size at the time of birth. Whereas this was an incognita a few years ago, the last simulations, the more precise simulations of the Boston group, they show that loops are always born are around a scale a tenth of the horizon. This alpha is a relative size to the horizon. So if I fix that as an input, then I can stick only to this prediction, which actually for once it favors the signal instead of going the other direction. And then we can think of what's the possibility of LISA, for instance, LISA, to measure this signal. And what you see is here different examples computed for different tensions, and there is a huge potential discovery, huge, of this signal, because there are orders of magnitude you can fit within the LISA power law sensitivity. So, in other words, if this is the prediction that we ascribe to cosmic strings, there is huge potential discovery, down to a tension of in Planck units of 10 to minus 17, which corresponds to a BEV of the order of 10 to 10 GeV. So from this point of view, we are going down in energy scale, getting as close as possible to colliders. We are not going to get close to colliders yet, but the idea is from cosmology, we are reducing the possibility of probing energy scales down to certainly smaller energy scales than GAT, which is this case. Good. So the constraint at CMB for the tension is 10 to minus 7. From pulsar time arrays is 10 to minus 11. And from future pulsar time arrays is at most 10 to minus 14. But for LISA, we are going to improve 10 orders of magnitude this signal from compared to CMB. From PTA, 6 orders of magnitude PTA today, and from future PTA, 3 orders of magnitude. So LISA is really, again, a fantastic machine to discover possibly cosmic strings. It will put the best constraints on cosmic strings by far. Actually, the only way to really probe such small tensions, and either we discover something and we put string in constraints. But of course, all of this depends on the modeling assumed. And here I'm assuming the pure Nambu-Goto thing. Good. So with this, I think we are concluding the survey of sources. Let me see how we are doing on time. Yeah. We've covered the core topics. I'm happy to take questions, and then we make a coffee break because I guess it's too much to talk in 3 hours in a row about gravitational waves. I see you a bit more sleepy than usual, but let's take 5 minutes for questions if you want to ask something, and otherwise we take the coffee break. Yes?
From particle emission,
yeah.
You could get also other probes of cosmic strings?
Can you repeat? Sorry, the acoustic is very bad from there.
Since it's like a cosmic strings,
Yes.
will you get also other probes via particle emission in some way? Or
Probes, you mean like could I probe that radiation emitted by the strings?
physically, or also like from...
Yes, I believe there is gamma rays associated production to cosmic strings. I haven't studied them, so I don't know what is the prospects of detectability. But what is really relevant for us is that if I have a channel of particle production, which is the material the strings are made of, then I'm gonna shrink the string, the loop, much faster than assuming only gravitational radiation. And that means that my loop number density is gonna significantly reduce itself. And hence the signal for a given tension is gonna be much smaller. You know, that's the natural consequence.
How much smaller would it be respect to...
Orders of magnitude. We are only finishing the characterization of particle production from the loops. We don't have the answer yet about the integrating that to get the background, but orders of magnitude for sure. I believe that if I take PTA constraints at face value, I'm gonna open up those, if I use PTA data, I'm gonna open up again the possibility of cosmic strings to go back to GAT scale. Because for GAT scale, my signal is gonna be weaker than what they thought from Nambu-Goto, and hence it's gonna be compatible with PTA. But the exact details, we haven't worked them out yet. Yeah. But we are on the way. More questions? Yes, please.
So for the particle emission from the cosmic string loops, would you expect such particle, like a dominant particle emission from other cosmic detectors, or would you expect that it's going to be just for strings?
It's just for strings, because it's a particular thing of the loops again. For instance, the long strings, they don't emit much particles, because in the moment they emit them, this smooths out the long string, and then you stop emitting them. They are really topologically stable. But these loops, because they are emitting particles, they go shrinking in size until they disappear. So it's something very characteristic of having loops. very, very characteristic of having loops. Yeah. Yes?
Do you think it's to be a bit model dependent, so that you could maybe propose a model when this particle production is subdominant to the gravitational wave emission?
Fantastic question. So in 2019, Tamei Vachaspati and collaborators, they put out a paper, the first paper, in which they isolated loops in field theory, and they studied their particle production. Okay? And how to create a loop in the lattice is very complicated, to isolate a loop. So they did the following technique. They took a Nielsen-Oleson analytic solution, so an infinite solution which is straight, okay? They put two of these tubes like this, and now they boosted them with certain velocity. And if I do the same with another pair of tubes here, and now I boost them with another velocity, so I make them cross by pairs, the result is going to be that they are going to intercommute, and they are going to produce a square loop and an external loop like this. Okay? This is, I have periodic boundary conditions, so you have to think this as a second loop. Forget about this one. Let's isolate this one, the internal one. They prepare configurations like this, and they measure the particle production. Okay? They measure the particle production, let's call it like this, power of particle production, and then they compare it with gravitational waves from Nambu-Goto. And what they got was a scaling in such a way with the length, with some power here, such that there is a critical length such that for L smaller than this critical length, then particle production dominates over gravitational waves. For scales larger than the critical length, they obtain that particle production becomes subdominant before versus gravitational waves. So this would be the situation you are asking me. So essentially in this picture, where I have these loops, the case is that for when they are small enough, particle production dominates. When they become macroscopic enough, cosmological enough, gravitational wave dominates, and I go back to Nambu-Goto picture. Now what's the problem with this? That these loops these loop shape are very artificial. They are a square shape. That's never going to happen in a phase transition. So what we asked ourselves last year is, what happens if I simulate a phase transition? Now I get, my infinite strings, which give rise to some loop configurations, and now I isolate one of these loops, coming from the actual realization of a phase transition. You get a loop like that. And now I ask, what is the particle emission from this loop? Okay, power of particle emission versus actual power from gravitational waves. And instead of using Nambu-Goto, I actually can compute also directly the gravitational wave emission. And here is the surprise we get, that when we do this exercise, power of particle production always dominates over gravitational waves for every length. And this is why, if this is the case, then I'm going to suppress so much the loop number density, because I'm going to decay the loops as I form them into particles, and they are not going to be there to oscillate as many times as you want for gravitational wave emission. Yes?
So you mentioned this paper by Tamei.
Yeah.
Do you find a similar power law?
For that? Yes. Yes. Yes, we reproduce this. We've produced a finer set of square loops, and we've probed different scales, and we find the results even more accurately. So it's absolutely correct what they say for this kind of loops.
But if I remember correctly, this gamma that you write here really depends on the small scale structure. Like if you have cross domination or king domination,
This gamma, well, in this case, there is only one type of loop, which have these kings, so this is king dominated, clearly, and that's the point. With these kings, and this configuration, it happens and we reproduce this, and we even did other type of artificial loops, and we always find that when you are kick dominated. But when you are in the kind of loops you get from a random realization of phases of your Higgs, we've done all kind of infrared and UV studies to see that this doesn't depend on the lattice, resolution. And we always get the same result, that up to a separation of lengths over the core of the string up to 3,500. Okay, this is our pool of loops. They are capable of separating length scales compared to the radius of the core scale 3000. We always have this result, We are not particularizing to how many kicks or caps I have here. It's just I'm taking the realistic realizations of these loops from a phase transition. And the result is this, and I have no reason to believe now, based on this scaling, that that's going to change at higher, at longer length scales.
I think my question was more in the direction of if you artificially construct one of these loops and artificially put in extra kicks or costs.
Yeah.
Like if you could tell me something about how the power would scale with the number of kicks you artificially put in costs.
We will be able to do that, okay? But just as I said, this we have not even published. Hopefully we can put it out end of this week or next week in the archive, okay? But the point is, these are the first studies to do that. Now, our next study will be to start looking at what are the features here causing the given emission. And then maybe I can introduce artificially a kin or a cusp there and start studying that. But for me, the relevant thing is that when I mimic a phase transition, this is what I get, And then anything other artificial is going to become a bit academic, very interesting, but, unless you produce a square loop in nature, that's not going to happen, And it's very interesting because it's really telling that because we've been using Nambu-Goto for 40 years, people have really neglected the idea that you could produce these particles. Then Tamei and his collaborators, they came with this nice idea, and this supported the Nambu-Goto for the long loops. Fantastic. But then we said, okay, you don't get those loops, let's try the real ones, and this is what we get. Now, there is a lot of work to do to understand why we get that and not something else, but I have no doubt that within the range of scales we can separate, which are not bad, because 3,500 is pretty decent. We get a very solid, robust result like this, which is going to impact abruptly in what is the expected background from from strings loops that produce particles. Now we have half an hour to deal with the late universe and observational point of view of the whole program I've been telling you. This tells you the bias I have as a theorist, if I'm dedicating only half an hour to the astrophysics part and observations. Let's start with astrophysics. After all we know about gravitational waves are the signals measured from astrophysical system. Compact binaries, mostly black holes, that are orbiting around each other. We have a plethora of them, of the order of 100 by now. They produce beautiful waveform signals that have been detected in the LIGO-Virgo network of detectors. Good. This means that there are many of these binaries in the universe, and we are only observing few of them. But from these few of them, we can infer statistically the properties of the whole distribution because we take them as representative samples. So essentially we can do this, of course, with a given error. Obviously it's not an exact reconstruction, but the more of observed ones we have, and this number is growing by the time, the better we are going to reconstruct the whole population. And hence the theoretical predictions we can make with that population. So most of the binaries in reality are unresolved because either they are too weak, so not so massive, or too far away from us. So you cannot see them individually as gravitational wave emitters, but that doesn't prevent the fact that they can join forces, and they produce altogether a gravitational wave background. By superimposing all the signals. It's a stochastic background because it comes from so many signals. At the individual level, we are not resolving them, but the superposition of all of them statistically is going to give you a background. This is called the astrophysical background. Good. This is either from black hole binaries neutron star binaries or white dwarfs, or whatever combination of these, if they can link together into a binary system. So let's do a bit of the math of the physics. Now we want to predict this background. Omega gravitational waves is the standard definition, but now I'm gonna link it, instead of in terms of my energy density spectrum, in terms of the strain, the typical amplitude, characteristic amplitude of my actual gravitational waves. Good. If I want to compute any signal coming from this, I of course need a modeling of the number of these guys per, for instance, unit of redshift, because I need to know how this evolves in cosmic history, even if it's the most recent cosmic history. Good. Well, it turns out that, well, before I do this, of course, we also need a prediction of what is the strain as produced in general if you were to know this distribution. And it turns out that this is very relatively simple to compute in general relativity. It was done by Finney already more than 20 years ago, and essentially the strain is an integral in time, here in redshift, over the distribution of these binaries times the actual energy spectrum they emit individually. So it's all very logical. I have a bunch of them, each of them emit a given spectrum, I sum them, this is what this integral in time over the number density means, and I'm gonna get the total strain today. Okay, and the actual formula is just this. Good. Now the question is, this spectrum is very simple to compute in general relativity. This is a typical textbook example that you do in the first chapter of gravitational waves. In general relativity, when you go to the chapter of gravitational waves, the first example they are going to give you is precisely what is the spectrum emitted to first order from one of these binary systems. Notice that I have to evaluate it here at the frequency at the moment of emission, and then I have to redshift it to the frequency today. Okay, one has to be careful with that little aspect. So this is the textbook answer. Of course, it's a lengthy calculation, but you can find it literally in any textbook that covers gravitational waves. And essentially it's telling you that the energy emitted per unit of frequency is somehow proportional to a fancy combination of masses. This is called the chirp mass. So it's degenerated in the two masses. It's not isolating one of the mass or the other in this funny combination, and then it goes to the fifth to 3 power. And also depends on the frequency in this manner. So if my frequency is high, then I'm going to suppress the signal. If the frequency is low, I'm going to enhance it. Okay, there is a spectral dependence on the frequency in that particular fashion. Good. So now comes more complicated problem, because that was theoretical problem, how to compute the spectrum emission from a single binary. Now comes the more complicated problem of where do I get this information? It's in a sense analogous to the problem of the cosmic strings before. Where do I get the loop number density? We get it from simulations. Now where do we get the number density of binaries? We need to somehow obtain it from observations. Basically, you can break down this guy always into what we call the merging rate, which tells you the number of events of merging per unit of time, times the mass distribution, which tells you the number of these binaries as a function of mass in the universe, or the probability, if you want to have a given two masses there. In the universe, no, you have binaries of very different masses. If I calibrate this somehow from simulations of observation, I should be able to predict how likely it is to get a given binary pair with given two masses. And then there is some cosmological factor. So the question is, we need to really pin down what is the merging rate and what is the mass function. And of course, this is what observations are telling us. So let's assume we know that. I plug it here, still written in an uncertain manner, and now I have my strain here. It's an integral over the mass function, so the probability of having a given binary pair with masses m1 and m2, you have to integrate over the masses, times integral of time of the rate of merging of these binaries times the production of the signal, of the given strength of gravitational waves. So, we are writing down our formalism to be able to make a prediction. So now I need to calibrate this mass function. It can be more complicated than what I'm telling you, of course, because the spins can be in the game, and I need the spin distribution as well. Let me ignore that for simplicity. We can think of black holes, as we said, neutron stars and white dwarfs. Good. For black holes, we can use the observations of LIGO Virgo. As I said, we have of the order of 100, so that's already enough to calibrate with certain errors what is the distribution of binary pairs in the universe. For neutron stars, we also have many observations on the optical, not on the gravitational wave side. And for white dwarfs, we also have many astrophysical observations. We can also use calibration from simulations, etc. Doesn't matter. The point is, assume I calibrate somehow my mass function. I'm going to show you now the exercise of calibrating this mass function with the observations of LIGO Virgo. Okay, I'm using the statistics that LIGO Virgo is telling me, and I'm just going to show you the result. And the result is this noisy background. So omega gravitational waves versus frequency, and essentially all this noise, in reality, if you resolve it a bit better in the frequency, if I integrate out, if I coarse grain this signal, you know, so noisy, what I really get is a power law as f to the 2/3. This was predicted by Finney, actually, in his famous paper in the early 2000s, because he already knew the functional form of the emission of a given binary pair, obviously, and then he could speculate with what is the functional frequency form of the background. What we are doing now is calibrating what is the signal based on the actual population of these guys in the universe according to LIGO Virgo observations. And why is it so noisy? Because we don't do the analytical formula here. What we do is to create a distribution numerically of these binary pairs, and we create many catalogs like this of literally thousands of binaries, and then we extract the individual signal of these binaries, and then we superimpose them. So we do the real thing with the simulated catalogs that sample the distribution according to the LIGO Virgo information. And this is why this is so noisy. It always shows you that reality is a bitch, and nothing of a power law really looks like that in reality, okay? What you really have is a very noisy thing, but in reality, the pattern shape is really this power law. And what's the problem here? It's pretty obvious, I hope you see. I'm putting here the Lisa sensitivity band. This is telling me that I'm gonna be contaminated from the solar mass order black hole binaries. Oh, that's a phone, yeah. Maybe it's mine. It's coming from here. Ah, yeah. Hello. Hello. Yeah. Oh, speaking nicht Deutsch, but I'm going to pass you with someone, no worries. Okay, that was interesting. So, we have this situation, which means this is a guaranteed foreground now from our ability to detect fundamental backgrounds. Now, if I show you a more smooth version of this with not the noise, essentially given the uncertainties in LIGO Virgo, we are capable of predicting that we are going to have a power law like this with this uncertainty band. This uncertainty is reflecting you the uncertainty in all the parameters in the distribution of binaries as reconstructed from the few examples we have from LIGO Virgo. This is the same done by another group, and okay, the scale is different, that's why it looks different, the signal, but it's pretty much the same. So this is good because two independent groups, now we obtain pretty much the same with the calibration from LIGO Virgo, which means that we are pretty certain that we have a problem in order to detect fundamental backgrounds. And now the community has to think how to deal with that. And look, I have another plot here. This is from white dwarfs. So it's even worse. We are expecting a very large contamination from white dwarfs, which are also gonna mask any fundamental signal in that frequency range. You know. That's why I don't like astrophysics. You know. Well, not really, I have other reasons. So, astrophysical background, so far so good. You know, the point is there are binaries in the universe. They gravitate, and they produce signals. Beautiful. This is how we've demonstrated we can detect signals, but now they are going to contribute to a background which is going to create us a problem. What about observational prospects and current constraints on gravitational wave backgrounds? So, gravitational wave observations, let me tell you 3 points about this. First of all, this is entering into a real game. When I was your age, I was playing only at the theoretical level. Oh, I have this model, I produce this spectrum. Okay, this you cannot do anymore, because if you do that, you are doing very little. The real problem is to know how these detectors are going to analyze these signals. And in doing that, you are going to have a superposition of all the signals, including these astrophysical backgrounds, and we have to infer how good we can reconstruct our fundamental signals on top of everything else is going to be there. So it's not enough you just do a prediction of a background anymore and just that. So we need to deal with data analysis, which of course there are experts working on this. For instance, many people from particle physics are jumping now into gravitational wave detection, importing the techniques they have already developed for many years in particle colliders now to gravitational wave detection. It was only very recently, a few years ago, 5 years ago, that the first tool to do a spectral reconstruction with LISA was put out. So this tells you that until 2019, all we were doing was taking the so-called PLS curve, and I was plotting a spectrum, and whenever the spectrum was going on top of the PLS, I was saying, oh, I have detection. That doesn't work like that. It's way more complicated than that. But if you have somehow knowledge about the noise of the experiment, for LISA there is certainly some calibrations expected, then you can use it to simulate what LISA detector is going to be like, and then you can inject a realization of your signal, of a stochastic background mimicking your signal, and then you can see how good you reconstruct it. For instance, this is an example of a phase transition, very strong, that we are reconstructed above the noise of LISA. But then, of course, well, one problem of this code is that it's only internal for the LISA collaboration, and because I personally do not share this kind of privacy policies, I decided to discuss with other colleagues of mine, why don't we make a freely available tool, for people to use for reconstruction of backgrounds. So now we've made two groups, two independent groups, my group in Valencia and the group led by Valérie Dong at CERN, software that is freely available, which is actually more powerful or faster than the other technique, based on machine learning techniques, where you can do arbitrary reconstruction. You can do a reconstruction of an arbitrary shaped background within LISA. We are hoping to generalize this to Einstein telescope and to many other experiments. As long as people can give us a parametrization of the noise, this can be adapted to any experiment. And this is the tool that I think people are going to end using to really do the parameter reconstruction. You can do arbitrary shape reconstruction. Here I have one of my stairway signals, 3 peak, you see, and it can be done. Or you can do parameter reconstruction if you have a given profile, a template for your signal, which is what in particle physics they do. Good. Signal separation. Now we should play the game of combining experiments. For instance, if you combine LIGO with LISA, you are going to be able to break certain degeneracies between the merging rate of binaries for the astrophysical signal and the string tension for the signal coming from string networks. So, of course, once we have a plethora of experiments working, we should take them all together and see how they affect each other. Or we should also start playing the game of how to reconstruct a signal on top of a foreground. Of course, if the signal is above the foreground, it's going to be relatively easy. The problem is going to be when my signal is below the foreground. What's going to be our capabilities to reconstruct it within whatever the capabilities of the given experiment you want to look at. Not clear. This is where the community of data analysis in gravitational wave backgrounds is discussing nowadays. We are running a workshop precisely in discussing these techniques in Valencia in December. Have a look in Indico if you are interested, because it's precisely one of the nexus where experimentalists, theorists, astrophysicists, pure theorists are coming together, because we need to put together all our power to really deal with this problem. How to really dig up, a fundamental signal out of the noise and foregrounds that are going to be there. It's pretty much what happened in the CMB in the 70s and 80s, where people put all together their efforts and 90s to really start digging up the physics of the CMB. This is the same, but with gravitational wave backgrounds. Constraints, actual constraints today. So before June 2023, imagine we are not in July 2024, we are before June 2023. This would be the picture I would give you. From the CMB, because we have not detected B modes, I can put all this shape constraint. So I know there are no gravitational wave backgrounds of any size inside this gray area. Why is it like this? You already learned it, because the tail of the spectrum from inflationary quantum vacuum modes goes up for the matter-dominated era. And CMB decoupling happens already after matter radiation equality, so you are mostly matter domination yet, and then you pick up all this shape. Good. PTAs before June, this is the solution, so this is the situation, there is no signal inside this triangle. Direct detection, this is LIGO Virgo, there is no detection of any background within this color region. And then there are these straight lines, which remember is what we call BBN or CMB constraints, which are simply based on the fact that I cannot have more relativistic species than a given amount, otherwise I change CMB or I change BBN rates. So this gives me a straight line and I cannot have anything above that, okay, by construction. What's the future looking like for you guys, you know, for the next 1-2 decades? This is very nice, it's very bright. There's a plethora of experiments planned. Some of them are approved and they are very realistic. SKA, LISA, Einstein Telescope, Cosmic Explorer that I didn't put there, more speculative, AEON. So essentially, you see, this is the map between gravitational wave amplitude, spectrum versus frequency, and we are start to covering all this area. Not fully, you know, but there are a lot of regions in color now. This is going to be the situation in 15-20 years from now, and these things are approved. Why? Because the community really realized that, you know, by putting into operation these detectors, we are going to map exactly all the gravitational wave signals from binaries, from astrophysics, and then hopefully we are going to start detecting fundamental signals. What's the situation even further in time, 40 years from now? Well, if we succeed in this phase, then probably people will want to build something called Big Bang Observatory, or some modification of it, which is like a new generation of LISAs with 3 LISA-like detectors, and presumably they claim, at least on paper, that they can reach a sensitivity close to 10 to minus 16, 17 in omega gravitational waves, which would be pretty amazing. Because maybe I could even open up the possibility of direct detection of gravitational wave background of vacuum fluctuations from inflation, assuming CMB makes a prediction in the detection in the next 10 years. Who knows? If not, in any case, this is just good news, but this is not going to happen. This costs a lot of money unless this thing successfully detects something interesting other than just astrophysical backgrounds. Good. Now, evidence for backgrounds in the present moment. There is an elephant in the room that maybe some of you are thinking about it, which is, well, PTA, pulsar time array experiments, have claimed a detection. Okay, and I'm pretty sure even if you don't work in gravitational waves, you have heard of this. If not, you are living in your bubble, you know, because this is really important discovery. So these pulsar time array collaborations, which are 4, American one, European and international, I think from various places based on Parker, and then the China collaboration. Last year, they announced the detection of a signal based on the fact that they have pulsars, and these pulsars can be correlated by pairs, and the correlation, the angular correlation in the sky, is such that if it fulfills a given pattern, this demonstrates that in between the pulsars and us, there is a stochastic background of gravitational waves. Okay? Why is that? Because if there was no correlation, then this will be flat. And if there was no gravitational wave background, then obviously they are not correlated, because they are just propagating in empty space because there is no background. But if there is a background, they all see the same background in their line of sight propagating towards us. That's what induces the correlation. This is called the Helling-Downs correlation, and to 3 to 4 sigma, depending on your interpretation and experiment, it has been measured actually by the 4 different collaborations. These are the data, it's way more noisy than we would like, and depending on the analysis and the collaboration, is between 2 to 4 sigma detection of this correlation. And it is this correlation that is evidence, a very good evidence on the existence, for the first time, of a gravitational wave background. Okay? Good. Now, what is this gravitational wave background? It turns out that in these frequencies, the one characteristic of PTAs, which are nanohertz, very small frequencies, we expect naturally a signal from the binaries of supermassive black holes. Why is that? Because in structure formation, when the galaxies are on their way to form, some of these galaxies can couple together and start orbiting around each other. In doing that, they end losing all the environment around, like the gas or the stars, if you want, and then the whole problem boils down to 2 supermassive black holes orbiting around each other. And given their sizable mass, the natural frequency is expected at this nanohertz. So essentially, this is a natural candidate to explain the evidence for the signal. But of course, nothing prevents us from speculating that this could be a cosmological signal. It's way more speculative, especially because at these frequencies, except for the case of cosmic strings, there is no natural way to place one of these cosmological signals within the nanohertz regime. And yet we went like crazy, all the theorists producing papers, of course, saying what kind of signal you could have. Okay. This is very likely an astrophysical signal. We don't know. More work should be done at the data level. No? More data should be acquired. But a priori, nothing prevents you from speculating with early universe. And of course, if that was the case, this would be a revolution. Because if we could really prove at some moment that this is due to early universe physics, this is literally as revolutionary as the CMB was in their moment. How to distinguish one from the other? Luckily, for the astrophysical signal, they expect very large anisotropies, whereas for the cosmological signals, we don't. So essentially, within the next 5 to 10 years, we believe that these experiments are going to be within the sensitivity of measuring these anisotropies, and if they measure them, then for sure it's astrophysical. It cannot be cosmological. How to distinguish cosmological signals among themselves? From the spectral shape. Right now, the spectrum is very poorly measured, but as time will go by, we will measure better and better the resolution of the spectrum. And if there are no anisotropies, then we are going to keep playing this game, and nothing prevents you from speculating with it, but as I said, it's very unnatural, except for the case of cosmic strings. Good. We are getting to conclude. I'm not sure how good I'm doing on time. Not bad, okay? 2 minutes. I'm going to need a bit more of 2 minutes, but not much more. Summary and outlook. What we've covered in these lectures is that for sure the universe is filled up of gravitational wave backgrounds, because everything gravitates, and it's very easy to think of something that repeats itself in the universe and then overlaps their signatures, their signals, and produce a background. There are astrophysical and there are cosmological from the early universe. We know that the early universe ones are the ones that have interest for high energy physics from the point of view of theoretical physics, or fundamental physics. We know the astrophysical ones are going to prove the population of binaries in the universe. And therefore, the cosmological backgrounds are the holy grail, really, in this game, because they will prove, if we can detect them, fundamental physics. But we also know the astrophysical ones are guaranteed, whereas the cosmological ones are a pure speculation. Unfortunately, there is no real reason whatsoever to really think that there's going to be any cosmological signal detection. All I've been telling you is interesting cases that have some parameter space that can give rise to an observable signal. But that's not guaranteed. I could be producing those signals and they are out of range of detectors, or maybe this phenomena didn't even occur in the early universe. It's all speculative. That's the freedom advantage and the disadvantage, that we don't know what to expect. However, the astrophysical ones are guaranteed. So even going to make our game more difficult, because not only this is speculative, now we're going to have to see how to dig up these signals on top of foreground signals from astrophysics that we know for sure they are going to be there. Good. Summary, early universe sources and late universe sources. Early universe is a unique opportunity to prove high energy physics, which otherwise is inaccessible. And in this sense is complementary and beyond particle colliders. And just because this is such a unique opportunity, despite the fact that I just told you there is no clear motivation to expect a signal, it's enough for people to really purchase this avenue because this opportunity is unique and quite powerful in case it gets realized into a real detection. We could really tell about the nature and observability of inflation. We could prove the equation of a state of the early universe after inflation. We could prove primordial perturbations at almost any scale in the universe. We could demonstrate whether cosmological actions, so-called audible actions, are there. We could really prove whether there is a strong enough phase transitions, whether primordial black holes exist, whether cosmic strings exist. You know, it's very interesting because we can really prove a lot of physics. It's not guaranteed, this physics, but we can really have a handle on it. On the other hand, the astrophysics is guaranteed. It's going to play a foreground, and it's going to help us also to determine population properties, properties of their anisotropies, cross-correlations between other probes, not just gravitational, and even properties of gravity itself. So I haven't discussed all these properties, but there is a bunch of people also interested in exploring to what extent I can exploit the prediction of these astrophysical backgrounds to really do something interesting. Okay, in summary, if there is detection of the very early universe signals, this is opening a new window, literally. This picture, I love it, you know, because it really shows, you know, a new transition that we could have in physics understanding. If there is detection, we are going to reach energies way above any terrestrial means that we can think of. We are going to prove fundamental physics and beyond the standard model scenarios that mostly are otherwise inaccessible through terrestrial means. And we are going to get as close as possible to the origin of the universe with any observational proof. It's a new window into the universe, and it's as revolutionary, if not more, than the CMB discovery, and the exploitation of the CMB is what really made modern cosmology, modern science, you know. And it's complementary to colliders, which are going to carry on the LHC program for a number of years, for at least 2 decades, you know, and maybe next generation of colliders. But what about we don't, you know, otherwise we don't discover a fundamental signal? Well, first of all, hopefully for consistency, we have to detect these astrophysical signals. We are saying there are a contaminant because we really expect them there, so they better be there. Otherwise, we don't understand anything. And yet, if we don't detect anything, from the lack of detection, we are going to put superb constraints on BSM scenarios. We are going to rule out entire families of scenarios. So in this 20 years perspective I show you with all those experiments, we will really detect nothing fundamental. This is going to give us a lot of information about how the universe was not. Okay? So that's why this is called the dawn of early universe gravitational wave cosmology. We are also celebrating a big meeting on this in Benasque, Spain in 2025, organized with Komatsu, Faciello and others. Have a look, it's announced somewhere in Inspire, you know, and we are going to put together everybody in the community working on this and start discussing the perspectives for the years to come. With this, I think I'm concluding really my early universe gravitational wave program. But before I conclude, 2 more slides. Final remarks. Since you are students, you know, you are realizing that working on this is becoming really multidisciplinary. You've got to know about particle physics, field theory, cosmology, astrophysics, detection, whatnot. Of course, at the individual level, please don't pretend to do everything at the same time. If you are interested in backgrounds, start with whatever direction here you want. So you could start with modeling, theoretical sources, you could start with astrophysical signal, etc. You know, don't pretend to do everything at the same time because that's going to be difficult. At the same time, be aware, especially for the hardcore theorists, for instance, this gentleman here, you know, that if you want to do predictions here, the game is played numerically nowadays. you are going to have to do lattice simulations. There's no way you are going to get this production of gravitational wave signals without numerics, okay? Really no way, with precision accuracy. And now we are in the era of gravitational wave astronomy, so you need precision. You cannot say anymore, oh, I have a sketchy background with this spectral shape. Nobody's going to care if you do that, okay? So you are going to need numerics, lattice simulations, and you are going to need analysis. For me, as a theorist, only 5 years ago, I started learning these analysis techniques. And of course, they are very powerful because at the end, they show you the whole game of how you really detect a signal and how you really put constraints. And finally, propaganda, which I hope is very useful. If you want to learn at a more technical level everything I've been saying, we put out a review 6 years ago with my collaborator, Chiara Caprini, and we cover all the sources I've told you about here and more. The review is growing very fast out of date because this is such a growing field that there is so many contributions every year that, you know, some of the new contributions are not reflected in the review. But if you are a beginner and want to start from scratch, I think this is the best place to start. And propaganda part 2, if you want to really go lattice numerics, we have created a code that is very versatile and powerful to do all kinds of simulations. From cosmic strings to gravitational wave emission or whatever you want, phase transitions, your nonlinear dynamics, preheating, whatever you want, okay? That's the point. This is a platform for you to learn to use the code, put your Lagrangian, and run your nonlinear dynamics. And of course, learning this is difficult, so we are offering a series of schools. The first one was in Valencia, in the beautiful city where I live. Probably none of you were there, I'm not sure. If not, we did a second school, which was online. So actually, you can find all the lectures now online. And if you want to come in person, we are deciding yet where to do the third school. It's going to be, it's going to be in 2025, because I'm exhausted this year and I cannot run another school. And actually, very likely, it's going to be in Korea. We've decided to go to Asian market and go to Korea, and hopefully we will bring Chinese, Japanese, and all Korean communities to a place in Korea that they are offering us to do in person the school. And finally, thank you very much for your attention. I hope you enjoy and you learned something, and of course, I'm open to questions now or at lunch. Thank you.